Mars hung silent in the dark as 3i Atlas drifted by, a stranger from the stars. The orbiter's camera opened its eye and blinked at something uncanny. No shimmering veil of dust, no cometary crown of light, only a faint ghostly smear, so alien it unsettled even seasoned astronomers. The response was swift. ESA's crown jewel, the JUICE mission, was ordered to turn aside and watch. What secret called for such urgency? What does that smudge in the void truly mean? Tonight, we follow the trail of riddles hidden in this first image, and if you stay with me, you'll see why it wasn't supposed to look this way, and why that matters more than anyone admits. Part 1. Title Hook and What Just Happened. On March 27th, 2025, the European Space Agency released an image that wasn't supposed to exist. Not because the technology failed or the observation window closed, but because what appeared in those pixels contradicted nearly everything astronomers expected from a comet passing through the inner solar system. The image came from ExoMars Trace Gas Orbiter, a spacecraft designed to sniff Martian methane, not photograph visitors from other stars. Yet there it was, a fuzzy dot suspended against the darkness, captured after stacking dozens of long exposures because the target was 100,000 times fainter than the Martian surface below. What struck observers immediately wasn't what the image showed, but what it didn't show. There was no tail, no sweeping plume of dust and gas stretching millions of kilometers behind the nucleus, no glowing arc tracing the comet's path through space. Just a compact blob of light, diffuse and eerily symmetrical, hovering in the frame like something that forgot how comets are supposed to behave. For context, textbook comets develop tails as they approach the sun. Solar radiation heats their icy surfaces, sublimating frozen volatiles into space, carrying dust particles along for the ride. The solar wind then pushes this material away from the nucleus, creating those magnificent tails we associate with cometary visits, the kind ancient civilizations interpreted as omens, the kind that grace astronomy posters and inspire wonder. 3i Atlas was supposed to do exactly that. It's an interstellar comet, the third confirmed visitor from beyond our solar system, detected inbound in July 2025 by the Atlas Survey Network. Its trajectory confirmed it originated elsewhere. Some other star's planetary system ejected this object millions of years ago, and now it's passing through our cosmic neighbourhood at 86 kilometers per second. By the time it reached Mars distance, roughly 228 million kilometers from the Sun, any respectable comet should be visibly active, tail streaming behind it like a banner announcing its presence. But 3i Atlas arrived silent and tailless, at least in the images captured by ExoMars. The nucleus itself remained unresolved, meaning the spacecraft couldn't distinguish the solid body from the surrounding coma, that envelope of gas and dust that typically envelops active comets. All ESA's instruments could confirm was that something was there, something glowing faintly, something exhaling a coma without bothering to grow a tail. Astronomers had expected spectacle. They got mystery instead. Harvard astronomer Avi Loeb had warned this might happen. In a series of Medium posts published weeks before the ExoMars observation, Loeb outlined anomalies he'd noticed in 3i Atlas's behaviour, unusual brightness variations, possible forward jetting, not aligned with solar, heating patterns, orbital characteristics that didn't quite fit standard cometary models. Loeb has form here. He famously proposed that Oumuamua, the first detected interstellar visitor back in 2017, might be artificial, perhaps a light sail or probe from an extraterrestrial civilization. The scientific community largely disagreed, favouring natural explanations like nitrogen icebergs or hydrogen outgassing. But Loeb's willingness to entertain exotic possibilities made him the go-to voice for what if this isn't just a comet speculation. So when 3i Atlas showed up looking nothing like predictions suggested, Loeb's earlier warnings gained traction. The central mystery crystallized into a single question that refuses easy answers. Why doesn't this object look like a comet, when everything about its trajectory and composition suggests it should? Is this merely an observational fluke? Perhaps the tail exists but points directly toward or away from our line of sight, rendering it invisible? Or are we witnessing something genuinely strange, an object that defies categorization because it doesn't fit the natural boxes we've constructed? ESA added fuel to the speculation by announcing something unexpected. the agency revealed it was retasking JUICE, the Jupiter Icy Moons Explorer, a €1 billion flagship mission currently en route to Jupiter to conduct a side observation campaign of 3I Atlas. Think about that for a moment. JUICE wasn't designed for comet science. Its instruments target icy moon surfaces and Jupiter's magnetosphere. Redirecting such a mission even briefly involves significant planning, risk assessment and justification. The fact that ESA deemed this worthwhile suggests the agency recognised something unusual enough to warrant deviation from mission parameters. An ESA statement accompanying the retasking announcement used carefully neutral language, noting the observation was unexpected for everybody, a bureaucratic way of acknowledging that 3I Atlas had surprised the scientific community. This urgency hints at something deeper. Perhaps initial data revealed characteristics that warranted immediate follow-up. Perhaps the lack of tail triggered concerns that this object might not be what it appears. Perhaps scientists simply recognised a rare opportunity to study an interstellar visitor with multiple spacecraft simultaneously. The speculation writes itself. If you were an advanced civilization wanting to send a probe to observe other star systems, how would you design it? Perhaps you'd coat it in ice and dust, camouflaging it as a natural object. Perhaps you'd minimise reflective surfaces to avoid detection until absolutely necessary. Perhaps you'd engineer it to release gases in a controlled manner, creating a coma for further disguise while avoiding the telltale tail that would mark you as obviously active. This is pure speculation, of course, entertaining but unproven. Yet the question lingers, because the data refuses to cooperate with simple, natural explanations. The anomalies aren't merely photographic curiosities. They extend into spectroscopy, polarimetry, dynamics. Every measurement seems to add another layer of strangeness, rather than resolving the mystery. And that's where this story truly begins, in the intersection between what we observe and what we expected to observe, between the reassuring predictability of celestial mechanics and the unsettling reality that sometimes the universe delivers objects that don't read the textbook. What happens when the data contradicts the theory? What do we do when an interstellar visitor refuses to behave? Those questions will drive everything that follows, as we dive deeper into the measurements, the controversies, and the possibility, remote but tantalizing, that 3I Atlas represents something beyond our current understanding of comets, debris, and the flotsam drifting between the stars. Part 2. Snapshot of observational timeline up to now. The story of 3I Atlas begins not with ESA's puzzling image, but months earlier in the systematic sweeps of robotic telescopes scanning Earth's skies for threats and curiosities. On July 1st, 2025, the Atlas Survey, Asteroid Terrestrial Impact Last Alert System, detected a moving object that didn't match known asteroids or comets. Within hours, preliminary orbital calculations revealed something extraordinary. This wasn't a solar system native. Its velocity vector and trajectory suggested interstellar origin, making it only the third confirmed visitor from beyond to pass through our cosmic backyard in recorded history. The discovery triggered immediate interest across the astronomical community. Interstellar objects are exceedingly rare, or rather, detecting them is exceedingly difficult. They move fast, appear faint, and give us limited observation windows before racing back into the darkness between stars. Oumuamua in 2017 caught everyone off guard, departing before detailed study could occur. 2I Borisov in 2019 provided better data, but raised new questions about cometary diversity. Now 3I Atlas offered a third data point, a chance to refine our understanding of what gets ejected from other planetary systems and how those objects behave during their brief passage through ours. Hubble Space Telescope observations began almost immediately after confirmation of interstellar status. The aging observatory, despite its decades in orbit, remains capable of exquisite photometry and spectroscopy. Early images showed a dim object surrounded by a faint coma, encouraging signs that 3I Atlas was active, sublimating volatiles as it approached the inner solar system. But something odd appeared in the colour indices, those ratios of brightness measured through different filters that reveal an object's composition and reflectivity. The colours didn't quite match typical comets, skewing slightly redder than expected, hinting at dust properties or compositions unlike what we see in solar system comets. Then James Webb Space Telescope turned its infrared gaze toward the visitor. JWST, humanity's newest and most powerful observatory, excels at spectroscopy, breaking light into component wavelengths to identify chemical signatures. The initial spectra revealed something surprising. Carbon dioxide dominated the coma gases by a factor of 8 compared to water vapour. This inverted ratio is unusual. Most comets we've studied show water as the primary volatile, with carbon dioxide playing a secondary role. Comets are often described as dirty snowballs, emphasising the water ice that forms their bulk. But 3I Atlas seemed to be exhaling carbon dioxide preferentially, suggesting either unusual composition or unusual sublimation dynamics driven by its interstellar heritage. As summer progressed into early autumn, 3I Atlas continued its inward journey, passing Mars' orbit in early October 2025. This proximity created an unprecedented opportunity. Mars hosts multiple orbiters: NASA's Mars Reconnaissance Orbiter and MAVEN, ESA's ExoMars Trace Gas Orbiter and Mars Express, all equipped with cameras and spectrometers. These spacecraft weren't designed for comet observation, but mission planners recognized the chance to capture an interstellar visitor from a unique vantage point. Observations were scheduled, telescope times negotiated, pointing maneuvers calculated. ExoMars Trace Gas Orbiter drew the assignment for high-resolution imaging using its CASIS camera system. The challenge was immediate and obvious. CASIS was designed to photograph Martian surface features, cliffs, craters, gullies, targets that reflect substantial sunlight and provide high contrast. 3I Atlas, by comparison, was 100,000 times fainter than typical targets. Capturing any usable image would require pushing the instrument to its limits, stacking multiple long exposures to build up enough signal above the noise floor. The process resembled astrophotography techniques used by amateurs imaging deep sky objects, except conducted by a spacecraft orbiting another planet, tracking a moving target millions of kilometers away. While spacecraft jockeyed for position, ground-based telescopes maintained continuous monitoring. Light curve measurements, tracking brightness variations over time, revealed a 16-hour periodicity suggesting the nucleus rotates every 16 hours, tumbling through space with modest brightness changes that hint at an elongated shape. These observations came from observatories scattered across Earth, coordinated through informal networks where astronomers shared data in near real time, recognizing that interstellar visitors demand collective effort given their fleeting nature. Throughout this timeline, Avi Loeb maintained a running commentary through Medium posts and interviews. He noted the lack of visible tail, even as 3I Atlas approached distances where sublimation should intensify. He questioned the brightness behavior, suggesting the object might be larger or more reflective than standard cometry models predicted. He drew parallels to Oumuamua's anomalies, building a case that interstellar visitors systematically defy our expectations, perhaps because they form under different conditions, or perhaps, he left this unsaid but implied, because not all of them are natural. The public followed along with interest amplified by recent history. Oumuamua had captured imaginations precisely because it seemed so strange. Its elongated shape, its tumbling rotation, its mysterious acceleration away from the sun without visible outgassing. Debates about its nature spilled from scientific journals into mainstream media, with headlines asking whether we'd detected our first interstellar artifact. 2I Borisov provided relief by behaving conventionally but also disappointment. Where was the exotic chemistry, the anomalous behaviour, the hint that something truly alien had visited? 3I Atlas seemed poised to split the difference, active enough to be clearly cometary, weird enough to sustain speculation. By late March 2025, anticipation built toward the ExoMars image release. Preliminary reports suggested the observation had succeeded despite technical challenges, that CASIS had captured something amid the noise and faintness. When ESA finally published the images, the astronomical community gathered around computer screens, expecting to see a comet doing what comets do, sublimating, streaming, trailing its ionic banner across the solar wind. Instead, they saw that compact tailless blob, fuzzy and enigmatic, refusing to perform on cue. The timeline reveals something important about modern astronomy. We live in an era where detection happens rapidly but understanding develops slowly. Within hours of discovery, we knew 3I Atlas was interstellar. Within days, spectra revealed unusual chemistry. Within weeks, light curves characterized rotation. But months later, fundamental questions remain unanswered. Is this a comet or something else? Why does it look wrong? What does its composition tell us about its origin? These questions persist because data alone doesn't provide understanding. Interpretation requires models, comparisons, debates, and often years of analysis before consensus emerges. And now, with ESA's image showing an object that defies easy categorization, the timeline enters a new phase. The mystery deepens rather than resolves, anomalies accumulate rather than clarify, and the possibility that 3i Atlas represents something genuinely unusual, whether naturally unusual or something more provocative, shifts from fringe speculation to legitimate scientific question. What comes next in this timeline will depend on observations still being planned, data still being analysed, and debates still being conducted in conference rooms and comment sections across the astronomical world. Part 3, the ESA ExoMars image, what it actually shows and doesn't. The ExoMars Trace Gas Orbiter image of 3i Atlas consists of multiple stacked exposures, each several seconds long, combined to build signal above the instrument's noise threshold. What emerges from this stacking is a faint point of light, not quite star-like, slightly fuzzy, definitely extended, moving against the background stars over the course of the observation sequence. The nucleus itself remains unresolved, meaning the camera couldn't separate the solid body from its surrounding coma. Everything we see is that envelope of gas and dust, that diffuse cloud extending perhaps a few hundred to a few thousand kilometres from whatever lies at the centre. The most striking absence is the tail. Comets develop two types of tails as they approach the Sun. The dust tail forms when solar radiation pressure pushes dust particles away from the nucleus, creating a curved arc that traces the comet's orbital path. The ion tail forms when solar wind, that stream of charged particles flowing outward from the Sun, strips ions from the coma and drags them straight away from the solar direction, creating a blue glowing spike that can extend millions of kilometres. Both tails should be visible for an active comet at Mars distance, assuming reasonable dust production and gas emission rates. 3i Atlas showed neither. The coma appeared symmetric, compact, lacking any elongation or directional streaming. No faint smudge extending in the antisolar direction. No subtle arc tracing the comet's motion. Just a fuzzy blob that could pass for an unresolved galaxy or nebula if you didn't know what you were looking at. ESA analysts examined the data carefully, applying various image processing techniques to enhance faint structures, but the tail refused to appear. If it existed, it was either below detection limits or pointed precisely toward or away from the spacecraft, foreshortened to invisibility by geometry. Tails matter because they're diagnostic. The amount of dust in the tail reveals production rates, how much material is being lost per second. The tail's shape indicates particle sizes and velocities. The tail's chemistry, captured through spectroscopy, identifies which molecules are sublimating and in what proportions. Without a visible tail, astronomers lose much of their ability to characterize the comet's activity. They're left inferring from the coma alone, which is trickier because the coma can be optically thick, hiding the nucleus, mixing multiple emission sources, and varying with viewing geometry. Technical limitations complicate interpretation. ExoMars Cassis operates at wavelengths optimized for Martian surface features, not faint cometary emissions. The camera's dynamic range and sensitivity, while excellent for its primary mission, struggle with objects 10,000 to 100,000 times fainter than normal targets. Noise becomes significant, random fluctuations in detector pixels that can mimic faint structures or obscure real features. Stacking multiple exposures reduces but doesn't eliminate this noise. Some fraction of the missing tail might simply be buried below detection threshold, invisible not because it doesn't exist, but because the signal-to-noise ratio is too poor to reveal it. Yet the symmetry of the coma is troubling. Even if the tail itself is invisible, you'd expect some elongation, some hint of directionality in the coma's outer regions where gas and dust transition from bound to unbound, where solar radiation begins pushing particles away. The coma looks almost spherical, suggesting either extremely low production rates, so low that particles hover near the nucleus rather than streaming away, or viewing geometry that perfectly conceals any asymmetry. Both explanations are possible, but require specific conditions that feel like special pleading. The coma's compactness adds to the puzzle. Typical cometary comae extend far beyond the nucleus, often tens of thousands of kilometres across, with brightness falling off gradually as you move outward. 3I Atlas's coma appears tighter, more concentrated, as if the gas and dust aren't spreading as efficiently as expected. This could indicate unusual gas velocities. Perhaps carbon dioxide sublimation produces slower expansion than water, or it could suggest unusual dust properties, particles that clump together or charge electrically, altering their dynamics. Public reaction to the image was immediate and predictable. Social media lit up with comparisons to Oumuamua, which also lacked a tail and sparked speculation about artificial origin. The word alien-like appeared in comment threads, though ESA carefully avoided such language in official statements. Scientists emphasized the technical challenges and observational limitations, urging patience and caution. But the image's strangeness was undeniable. This wasn't what a comet should look like, at least not according to models and expectations built on decades of studying solar system comets. But there's another possibility that astronomers discuss quietly, reluctant to elevate it to hypothesis status without more evidence. What if 3I Atlas isn't primarily a comet? What if it's a solid body, rocky, perhaps with ice mixed in, that outgasses weakly, creating a coma without the vigorous sublimation needed for tail formation? This would make it more asteroid-like than comet-like, though the distinction blurs at interstellar scales, where objects might not fit neat solar system categories. Oumuamua faced similar classification debates, ultimately labelled a comet by some, an asteroid by others, and we don't know by many. The upcoming JUICE observations carry significant weight precisely because they offer another vantage point, another set of instruments, another opportunity to catch tail formation if it's delayed or intermittent. JUICE will observe 3I Atlas at different solar distances, different angles, different wavelengths. If the tail appears then, the mystery resolves toward natural explanations. Geometry or timing concealed it from ExoMars. If the tail remains absent, the anomaly deepens, demanding more creative explanations for why an object clearly outgassing refuses to display the signature feature of cometary activity. Speculation inevitably drifts toward more provocative explanations. If 3I Atlas were artificial, a probe, a sail, a defunct piece of technology, how would we expect it to look? Probably not like a sleek spacecraft from science fiction. More likely it would be coated in dust accumulated over millions of years of interstellar travel, perhaps intentionally covered to blend in, perhaps just naturally ablated by micrometeorite impacts and cosmic rays. It might outgas from volatile ices on its surface or interior, creating a coma that masks its true nature. It might lack a tail if its outgassing isn't driven by solar heating but by internal processes, venting gases in ways that don't align with the anti-solar direction where tails form. This is rank speculation, entertaining but unproven. The scientific consensus remains that natural explanations are overwhelmingly more likely. Comets are common, interstellar ejection is common. Unusual compositions are expected given the diversity of planetary systems across the galaxy. Invoking artificial origin requires extraordinary evidence, not just anomalies, but anomalies that defy all natural explanations, coupled with positive signs of artificiality like geometric structures, coherent signals, or impossible materials. Yet the image sits there, refusing to fit expectations, challenging comfortable assumptions about what interstellar visitors should look like. And perhaps that's the real message, the real lesson from ExoMars, that our models are built on limited data, that every new interstellar visitor will teach us something unexpected, that the galaxy is stranger and more diverse than our provincial solar system experience has prepared us to expect. The tail might appear tomorrow, resolving everything into mundane normality. Or it might never appear, leaving us to puzzle over an object that behaves just oddly enough to keep wonder alive, to maintain that tantalizing gap between what we observe and what we understand. Part 4. The JUICE retasking, why it matters. The Jupiter Icy Moons Explorer wasn't supposed to be looking at comets. JUICE launched in April 2023 with a singular mission: study Jupiter's icy moons, Ganymede, Callisto, Europa, searching for subsurface oceans, analysing surface compositions, mapping magnetic fields. The spacecraft carries 11 instruments optimised for planetary science at Jovian distances, not cometary science in the inner solar system. Its trajectory takes it on a complex cruise involving multiple gravitational assists before arriving at Jupiter in 2031. Every maneuver is choreographed years in advance, every observation window allocated, every joule of propellant budgeted against mission objectives. So when ESA announced it was redirecting JUICE to observe 3I Atlas, eyebrows rose across the space science community. This wasn't a trivial decision. Retasking a flagship mission involves risk assessments, engineering reviews, instrument calibration checks, and most importantly, justification. Why spend resources on a target outside the primary mission scope? What scientific value justifies the operational complexity? ESA's willingness to proceed signals something important. The agency recognised 3I Atlas as an opportunity too valuable to ignore, despite the costs and challenges. The timing works in JUICE's favour. The spacecraft is currently cruising through the inner solar system during its first Earth flyby phase, passing relatively close to 3I Atlas's trajectory. The observation won't require major propulsive manoeuvres, just attitude adjustments to point instruments at the target. The distance will be substantial, millions of kilometres, but JUICE's cameras and spectrometers are designed for planetary scales and can resolve details invisible to ground telescopes. The observation window extends over several days, allowing multiple passes and different viewing angles as both spacecraft and comet move through their respective orbits. What can JUICE provide that other observatories can't? Multi-filter imaging for one, capturing the coma and potential tail in visible and near-infrared wavelengths simultaneously, revealing colour gradients that diagnose dust composition and particle sizes. Spectroscopy for another, using instruments like MAGIS and UVS to analyse coma chemistry in more detail than previous observations allowed. Time series photometry tracking brightness variations that might correlate with rotation or episodic outgassing events. Polarimetry measuring how light scatters off coma dust, providing clues about particle structure and composition. The symbolic meaning shouldn't be underestimated. ESA operating a €1 billion mission isn't done lightly or impulsively. The decision to retask JUICE reflects institutional judgment that 3I Atlas warrants serious scientific attention. It's a vote of confidence in the object's importance, a signal to the broader community that this isn't merely public curiosity or media hype, but a legitimate target for flagship-class resources. When ESA's official statement described the observation as unexpected for everybody, the subtext was clear: we've been surprised, we're taking this seriously, we're allocating top-tier assets because something here deserves it. Past comet missions provide context for what JUICE might achieve, even from distance. Rosetta-orbited comet, 67 Pochuryumov-Gerasimenko for 2 years, revealing intricate details of cometary geology, outgassing and evolution. Deep Impact crashed a probe into Tempel 1, exposing subsurface ices and studying the ejected plume. Stardust collected dust samples from Wild 2 and returned them to Earth for laboratory analysis. These missions transformed our understanding of comets, from astronomical abstractions into complex dynamic worlds. JUICE won't achieve that level of detail with 3I Atlas. The distances are too great, the exposure times too limited, but even crude characterizations would advance knowledge significantly. The specific scientific questions JUICE might address are tantalizing. Will the tail become visible from a different angle, resolving the mystery as simple geometry? Will coma chemistry shift as the comet approaches perihelion, revealing how interstellar ice compositions respond to solar heating? Will there be unexpected emissions, perhaps molecular species never seen in solar system comets, signatures of exotic chemistry from the thick disk environment where 3I Atlas originated? Will polarimetry confirm or refute the unusual dust properties suggested by earlier measurements? There's also the possibility of detecting delayed or episodic activity. Comets don't always behave smoothly. They can exhibit sudden outbursts where sublimation accelerates abruptly, perhaps triggered by subsurface pressure buildup, ice cliff collapses, or rotation bringing fresh material into sunlight. If 3I Atlas is hovering at the threshold of visibility, barely active enough to create a coma but not vigorous enough for clear tail formation, then a sudden increase in activity could produce dramatic changes observable by JUICE. The tail might switch on like a light, transforming the object from anomaly to conventional comet in hours. Speculation about ESA's internal motivations is revealing. The agency didn't have to make the JUICE retasking public. Many spacecraft observations are scheduled quietly, appearing in data archives weeks or months later without fanfare. ESA chose to announce this one, suggesting they wanted community awareness, perhaps to prepare other observatories to coordinate, perhaps to manage expectations about JUICE's primary mission timeline, perhaps to demonstrate responsiveness to emerging scientific opportunities. The publicity itself is a data point, indicating ESA views 3i Atlas as significant enough to warrant transparency. There's also a competitive element, though scientists rarely frame it this way publicly. Multiple agencies and facilities are observing 3i Atlas, Hubble, JWST, ground telescopes worldwide, Mars orbiters. ESA's decision to throw JUICE into the mix ensures European involvement at the flagship level, securing data rights and author positions on future papers, maintaining ESA's profile in interstellar object research. Space agencies are collaborative but also conscious of visibility and scientific credit. JUICE observations will produce papers with ESA author lists, presentations at conferences, press releases celebrating European contributions. The public reaction to the retasking announcement was encouraging. People understood the implications. If a €1 billion Jupiter mission is being redirected, something genuinely interesting must be happening. The narrative shifted from scientists are mildly curious to scientists are scrambling to observe. This urgency, whether real or perceived, feeds the sense that 3i Atlas is special, that whatever anomalies appeared in initial data merit immediate follow-up, that the window for understanding might close quickly if we don't mobilize resources now. What JUICE ultimately reveals remains uncertain, contingent on viewing geometry, instrument performance, and the object's behavior. The optimistic scenario has JUICE capturing clear images showing tail formation, spectroscopy confirming typical cometary chemistry, shifted by interstellar heritage, polarimetry explaining dust properties through natural mechanisms. The observations would demystify 3i Atlas, placing it firmly in the category of interesting natural object, while closing the door on exotic speculation. The pessimistic scenario, or perhaps optimistic depending on your appetite for mystery, has JUICE confirming the anomalies, showing a persistently tailless object with unusual chemistry and dust properties that defy simple explanations, deepening the puzzle rather than resolving it. Either way, the fact that ESA deemed this observation necessary tells us something important. The agency isn't in the business of chasing every astronomical curiosity with flagship missions. Resources are limited, competition for observation time is fierce, justifications must be rigorous. That JUICE got retasked means someone at ESA looked at preliminary data, recognised something worth investigating, and convinced decision-makers that the science justified operational complexity. Whether that recognition proves prescient or overly cautious will become clear in the coming weeks, as JUICE data flows down and analysts begin the painstaking work of extracting signal from noise, truth from artifact, and understanding from observation. Part 5. Loeb's Anomalies. Reminder and relevance to this new image. Avi Loeb has never been shy about asking uncomfortable questions. The Harvard astronomer built his early reputation on mainstream astrophysics, black holes, early universe cosmology, first stars before pivoting toward technosignatures and the search for extraterrestrial intelligence. His 2018 paper proposing Oumuamua might be artificial rather than natural made him simultaneously famous and controversial, celebrated by those who appreciate bold thinking, criticised by those who value caution. When 3i Atlas appeared, Loeb was primed and ready to scrutinise it for anomalies, publishing a series of Medium posts that catalogued oddities visible even in preliminary data. The first anomaly Loeb highlighted was the lack of tail, even in early ground-based observations. Most comets show at least faint tail development by the time they cross Mars orbit, assuming they're actively sublimating. 3i Atlas showed nothing. Some observers reported possible faint elongation in certain images, but nothing definitive, nothing that couldn't be attributed to noise or processing artifacts. Loeb noted this absence aligned with Oumuamua's behaviour, another interstellar visitor that produced no visible tail, despite passing close to the Sun where any ice should vaporise vigorously. The second anomaly involved what Loeb termed forward jetting, detailed astrometric measurements, precise tracking of 3i Atlas's position against background stars suggested small deviations from purely gravitational motion. These non-gravitational accelerations are common in comets, caused by gas jets erupting from the rotating nucleus that act like tiny rocket engines, nudging the object slightly off its predicted path. but the direction of 3I Atlas's acceleration didn't align neatly with the anti-solar direction, where you'd expect maximum heating and sublimation. Instead, it appeared more forward-directed, as if something were pushing the comet along its trajectory rather than perpendicular to it. This matters because natural outgassing from solar heating should produce forces roughly perpendicular to the Sun-comet line, assuming the nucleus rotates and jets fire from various locations as different regions rotate into sunlight. Forward-directed acceleration is harder to explain naturally, requiring specific combinations of rotation axis, orientation, and jet locations that feel contrived. Loeb suggested this might indicate controlled propulsion, a provocative claim lacking direct evidence but consistent with his general willingness to entertain artificial origin hypotheses. The third anomaly concerned brightness and cross-section. 3I Atlas appeared brighter than expected for a comet of estimated size, suggesting either the nucleus is larger than initially thought, its albedo is higher than typical comets, or light scattering from the coma is unusually efficient. Loeb noted that brightness anomalies can arise from geometric effects. A flat object like a sail reflects more light than a sphere of equal mass, or from active surface coatings that enhance reflectivity. He stopped short of claiming this proved artificiality, but emphasized that brightness exceeding predictions demands explanation, especially when combined with other anomalies. The fourth anomaly involved orbital geometry. 3I Atlas's trajectory brings it unusually close to the ecliptic plane, the plane where solar system planets orbit, compared to previous interstellar visitors. Oumuamua approached from roughly perpendicular to the ecliptic, as did 2I, Borisov, consistent with random arrival from any direction in space. 3I Atlas's near-ecliptic trajectory is statistically less probable by random chance, though not impossibly so. Loeb suggested this might indicate targeted arrival, an object whose trajectory was deliberately chosen to pass through the region where planets and potential civilizations concentrate. Now we can assess how the ExoMars image relates to these anomalies. The lack of visible tail directly confirms Loeb's first observation, lending credibility to his early warnings that 3I Atlas wasn't behaving normally. The coma's compactness and symmetry align with weak or absent outgassing, consistent with the second anomaly about unusual acceleration directions. The unresolved nucleus prevents testing the brightness anomaly definitively, but the coma's faintness, despite strong predicted activity, supports the idea that something about this object's light production or scattering differs from conventional comets. It's crucial to note that anomaly consistency doesn't equal proof of artificial origin. Multiple natural explanations exist for each oddity. The lack of tail could be geometry or low production rates. Forward acceleration could result from specific rotation configurations. Brightness could reflect albedo variations or dust properties. Orbital geometry could be random chance, after all. With only 3 interstellar visitors detected, we have no basis for strong statistical claims about typical trajectories. Scientific pushback against Loeb's interpretations has been vigorous but respectful. Most astronomers acknowledge the anomalies while favouring natural explanations. They note that faint tails can be masked by observation limitations, signal-to-noise ratios below detection threshold, contamination by background stars or galaxies, temporal variations where the tail appears only intermittently. They emphasize that unusual doesn't mean impossible, that nature produces surprising configurations all the time without requiring intervention from intelligence. The tension between public perception and scientific caution creates an interesting dynamic. The public, primed by decades of science fiction and recent headlines about Oumuamua, wants aliens. Every anomaly gets interpreted as potential evidence of extraterrestrial technology. Every unusual measurement sparks speculation about probes and artifacts. Scientists, trained to exhaust natural explanations before invoking extraordinary claims, resist this rush to cosmic significance. They see low signal-to-noise data, complicated systematics, and insufficient measurements to draw firm conclusions. Loeb occupies a unique position in this dynamic. He's credentialed enough to be taken seriously, Harvard professor, hundreds of peer-reviewed papers, former chair of astronomy department, but willing to speculate publicly in ways most academics avoid. His Medium posts and interviews provide the speculation that mainstream science journals won't publish, the what-if narratives that engage public imagination. Critics accuse him of seeking attention, of damaging astronomy's reputation by lending credence to fringe ideas. Supporters praise him for asking questions others fear to ask, for pushing Overton windows and encouraging open-mindedness. What makes Loeb's involvement with 3i Atlas significant is that his earlier warnings now appear prescient. He said to watch for tail absence. ExoMars confirmed it. He noted brightness oddities, the unresolved nucleus and faint coma support continued mystery. He suggested non-solar driven acceleration. Astrometric analyses remain ambiguous. Whether these confirmations vindicate his skepticism of natural explanations or simply demonstrate good observational skills depends on your priors about extraordinary claims and extraordinary evidence. The coming sections will dive deeper into the data that Loeb highlighted. Spectroscopy revealing chemical oddities, polarimetry showing unusual light scattering, dynamics that refuse to fit standard models. Each dataset adds texture to the mystery, either resolving anomalies through natural mechanisms or compounding them into a pattern that demands explanation. The question isn't whether 3i Atlas is strange. It clearly is. But whether that strangeness reflects natural diversity we haven't encountered before, or something genuinely beyond our current framework for understanding cosmic debris. And as ESA's image showed, sometimes the most important observations aren't what they reveal, but what they conspicuously fail to show. Like a tail that should be there but isn't. Like a visitor that looks almost right but not quite. Like a puzzle piece that doesn't fit no matter how hard you press it into place. Part 6. Spectral and compositional clues. Chemistry tells stories that images alone can't reveal. When James Webb Space Telescope trained its near-infrared spectrograph on 3i Atlas in September 2025, it wasn't looking for tails or nuclei, it was dissecting light, breaking incoming photons into component wavelengths to identify which molecules were present in the coma and in what proportions. Spectroscopy is astronomy's most powerful diagnostic tool, capable of revealing temperature, composition, velocity, even magnetic field strength, all encoded in patterns of bright emission lines and dark absorption features spread across the electromagnetic spectrum. What JWST found immediately caught attention. Carbon dioxide dominated the coma emissions by a factor of 8 compared to water vapour. For context, typical solar system comets show the opposite ratio. Water usually dominates, comprising 60 to 80% of sublimating volatiles, with carbon dioxide and carbon monoxide trailing as secondary species. This inversion is unusual but not unprecedented. A handful of solar system comets show carbon-rich compositions, particularly those originating from the distant Oort cloud where formation temperatures differed from the warmer inner regions where most comets coalesced. But 3i Atlas isn't from the Oort cloud, it's interstellar, formed in another star's planetary system under potentially radically different conditions. The carbon dioxide dominance could reflect its parent system's chemistry, perhaps a star with different metallicity, different carbon to oxygen ratios in its protoplanetary disk, different temperatures in the comet formation zone. Alternatively, it could indicate preferential loss of water during the millions of years 3i Atlas spent in interstellar space, where cosmic rays and ultraviolet photons from distant stars slowly process surface ices, breaking molecular bonds and allowing lighter molecules like water to escape, while heavier species like carbon dioxide remain trapped. The spectra also revealed weak signatures of other molecules, carbon monoxide, perhaps traces of methane, possible hints of more complex organics. The signal-to-noise in these detections was marginal, requiring careful analysis to distinguish real features from instrument artifacts or contamination from foreground sources. But if confirmed, these detections would paint a picture of chemical complexity, an object carrying not just simple ices, but potentially prebiotic molecules, organic compounds that in different circumstances might serve as building blocks for life. Dust signatures in the spectrum added another layer of mystery. Reflected sunlight from dust grains in the coma showed an unusual red slope, meaning longer wavelengths reflected more efficiently than shorter ones, creating a colour shift toward the red end of the spectrum. Solar system comets typically show flatter or neutral slopes, with dust grains reflecting sunlight relatively uniformly across visible wavelengths. The red slope suggests either unusual dust composition, perhaps carbon-rich grains, organic residues, or iron-bearing minerals, or unusual grain sizes, with larger particles scattering light differently than the fine dust typical of most cometary comae. Polarimetric observations added yet another puzzle. Polarimetry measures how light becomes polarized as it scatters off dust grains, with the degree and direction of polarization revealing information about grain shape, size, and composition. A European consortium conducted polarimetric monitoring of 3I Atlas, using several medium-sized telescopes, tracking how polarization changed with phase angle, the angle between Sun, comet, and observer, as 3I Atlas moved through its orbit. The results were striking. 3I Atlas exhibited a deep negative polarization branch at small phase angles, reaching -2.7% at around 17 degrees. This technical jargon translates to a specific scattering behavior. When sunlight hits the dust at certain angles, it becomes polarized in the plane perpendicular to the scattering plane rather than parallel as typically occurs. The depth of this negative branch, how negative the polarization becomes, and the inversion angle, where polarization switches from negative to positive, both provide diagnostic information about dust properties. Most solar system comets show negative polarization branches around -1 to -1.5%. 3I Atlas's -2.7% significantly exceeds this range, suggesting dust properties outside the normal distribution. Theoretical models link deep negative branches to highly porous fluffy aggregates, dust grains composed of tiny subparticles loosely bound together, filled with voids and gaps that enhance certain scattering behaviors. Alternatively, the unusual polarization could indicate compositional differences, perhaps silicate mixtures not common in solar system dust, or organic coatings that alter surface reflectivity. The combination of spectroscopy and polarimetry paints a picture of an object that's chemically and physically distinct from typical comets. The carbon dioxide dominance suggests formation in a different environment or processing by different mechanisms than solar system comets experience. The unusual dust, red-sloped, deeply polarizing, indicates either exotic composition or unusual structures that don't match our baseline understanding built on decades of studying solar system comets. Some scientists have proposed that these differences simply reflect interstellar heritage. After all, we've only studied 3 interstellar objects in detail, far too small a sample to establish what's normal for bodies ejected from other planetary systems. Perhaps every interstellar visitor will show chemistry and dust properties that deviate from solar system norms, reflecting the diversity of star formation environments, planetary disk compositions, and evolutionary histories across the galaxy. If 3I Atlas seems weird, maybe it's because our reference frame is provincial, limited to one star's debris field. But there's a speculative alternative that refuses to die, no matter how many times natural explanations are invoked. What if the unusual dust is unusual because it's engineered? What if the polarization properties reflect not natural mineral grains but manufactured particles, perhaps carbon composites, engineered aggregates, reflective coatings designed for specific optical properties? This is pure speculation, unsupported by any direct evidence, but it lingers in the space between data and interpretation, asking uncomfortable questions about how we'd recognize artificial materials if we encountered them. The spectroscopic detection of organics, if confirmed, adds fuel to speculation. Organic molecules are common in space. Amino acids have been found in meteorites. Complex hydrocarbons detected in interstellar clouds. Molecular precursors to life identified on comets and asteroids throughout the solar system. Their presence on 3I Atlas wouldn't be surprising, but it would be tantalizing, especially if the molecular inventory turns out to differ from solar system organics, suggesting different synthetic pathways, different chemical environments, perhaps even, though this is an enormous leap, different biological origins if the object passed through a system hosting life. The dust question connects directly to the missing tail mystery. If dust grains are unusually large or have unusual optical properties, they might not scatter light efficiently in the tail region, rendering it invisible despite being physically present. Alternatively, if dust production is dominated by large particles, those particles would fall back to the nucleus under its weak gravity, rather than being swept into a tail by solar radiation pressure. The tail wouldn't form not because sublimation isn't happening, but because the resulting dust never escapes the nucleus's gravitational influence. This natural explanation is elegant and plausible. It requires no exotic physics, no artificial intervention, just unusual but permitted grain properties. Many astronomers favour this interpretation, seeing it as the simplest resolution to the tail absence and polarisation anomalies. But simplicity isn't proof, and the sheer accumulation of unusual but permitted features — carbon dioxide dominance, red dust slope, deep polarisation, missing tail, forward acceleration — creates a gestalt sense of strangeness that exceeds what you'd expect from random variation. The chemistry of 3I Atlas potentially reveals its birthplace, offering clues about the stellar environment that spawned it. Recent modelling work, which we'll explore more deeply later, suggests 3I Atlas originated in the Milky Way's thick disk, an ancient metal-poor population of stars orbiting the galactic centre, in a puffed-up distribution above and below the thin disk where our Sun resides. Thick disk stars formed 8 to 12 billion years ago, during an earlier epoch of galactic history when the interstellar medium had different chemical composition, fewer heavy elements, different molecular abundances. If 3I Atlas truly originated from a thick disk star, its unusual chemistry makes more sense. Low metallicity environments produce different mineral condensation sequences, different ice compositions, different organic inventories than the relatively metal-rich environment where our solar system formed 4.6 billion years ago. The carbon dioxide dominance could reflect formation around a carbon-rich star, or in a disk where oxygen was preferentially locked into silicates rather than water ice. The unusual dust could be exactly what you'd expect from ancient, chemically primitive materials processed over billions of years of cosmic ray bombardment. This context elevates 3I Atlas from curiosity to treasure. If it's genuinely carrying fossil chemistry from the thick disk, it's a sample of galactic conditions from epochs we can otherwise only study through indirect observations of distant stars and ancient stellar populations. Laboratory analysis of returned samples, a goal currently far beyond our capabilities but perhaps achievable in future decades, could reveal isotopic ratios, mineral structures, organic molecules that tell stories about what the galaxy was like when it was young, what chemical pathways operated before the universe had been enriched with supernovae products from multiple stellar generations. But for now, we're limited to remote sensing, to spectroscopy and polarimetry, and imaging from millions of kilometres away. These tools have revealed an object that doesn't fit comfortable categories, that accumulates anomalies faster than explanations, that tantalises with hints of chemical exotica while withholding definitive answers. The next observations from JUICE, from ground telescopes as 3I Atlas passes perihelion, from continued Hubble and Webb campaigns, will either resolve these mysteries through patient data accumulation, or deepen them by confirming that yes, this object really is as strange as it looks, and no, we don't fully understand why. Part 7. Spin, light curve, dust activity, and the missing tail. Objects in space rarely sit still. They spin, tumble, wobble, and precess, their rotation axes tracing complex paths through inertial space as internal masses shift and external torques accumulate. For comets, rotation is diagnostic. It reveals shape, controls outgassing patterns, and determines how jets push the object off its gravitational trajectory. Understanding 3I Atlas's rotation became a priority for observers worldwide, requiring weeks of continuous photometry as the object moved through its orbit, measuring brightness variations that encode rotational information. A Spanish-led team published the first detailed rotational analysis in late October 2025. Their data came from multiple observatories spanning several longitudes, allowing continuous coverage as Earth rotated, preventing gaps that would complicate period determination. The light curve, brightness plotted against time, showed a clear 16.16-hour periodicity, with amplitude variations of about 0.3 magnitudes. In plain language, 3I Atlas completes one rotation every 16 hours, and its brightness changes by about 30% between maximum and minimum during each rotation. This amplitude reveals shape information. A perfect sphere would show no brightness variation regardless of rotation. Every orientation looks identical. Elongated objects show brightness changes because their cross-section varies as they spin, presenting sometimes their broadside, sometimes their narrow end to the observer. The 0.3 magnitude amplitude suggests modest elongation, perhaps axis ratios around 1.3 to 1, not dramatically. Cigar-shaped like Oumuamwa's estimated 10 to 1 ratio, but noticeably non-spherical. The rotation period itself is unremarkable for comets. Solar system comets span periods from hours to days, with 16 hours sitting comfortably in the middle range. This argues against exotic explanations like artificial structures, which might spin faster if they're meant to generate artificial gravity, or not at all if they use stabilization systems. 3I Atlas tumbles like a natural object should, governed by angular momentum conservation and torques from outgassing jets that slightly alter rotation over time. But the light curve hides additional complexity. Close examination reveals subtle deviations from a perfect sinusoidal variation, hints of a secondary period, possible brightness fluctuations uncorrelated with rotation, occasional sharp features that might indicate discrete outgassing events. These deviations are near the noise limit, requiring careful analysis to distinguish real variations from atmospheric seeing effects, instrumental systematics, or contamination from background stars that happen to fall near 3I Atlas in the images. If confirmed, these deviations would indicate that 3I Atlas isn't a simple, inert body spinning uniformly. Instead, it's actively outgassing in ways that vary with rotation, perhaps with discrete jets that switch on, as specific regions rotate into sunlight, perhaps with surface features, cliffs, pits, fractures, that create localized sublimation hotspots. This would be entirely consistent with natural cometary behavior. Missions like Rosetta revealed that comet nuclei are geologically complex, with varied terrain producing spatially and temporally variable outgassing. Dust production estimates add another dimension to the puzzle. By analysing the light scattered from the coma and comparing it to models of dust scattering efficiency, researchers estimated that 3I Atlas was losing mass at rates between 0.3 and 4.2 kilograms per second. This is small compared to typical comets approaching the Sun. Bright, active comets can shed hundreds of kilograms per second, even tons per second at perihelion, producing spectacular tails visible to the naked eye. 3I Atlas's modest production suggests either low activity, minimal sublimation because the nucleus is depleted in volatiles, or that most of the outgassing doesn't carry dust efficiently. The discrepancy between gas emission and dust production is telling. Spectroscopy confirms gas is present. Carbon dioxide dominates. Water is detectable. Other volatiles appear in trace amounts. But the dust, which should be lifted by gas drag as ices sublimate, remains largely absent from the tail region. Why would gas escape without carrying dust along? Several mechanisms could explain this disconnect. One possibility involves grain size. If dust particles are predominantly large, millimetre-sized rather than micron-sized, they'd be too massive for gas drag to accelerate them beyond the nucleus's escape velocity. They'd be lifted briefly, hover, then fall back, never escaping into the tail. This would create a coma filled with large grains near the nucleus, but no extended tail because particles never reach the distances where solar radiation pressure dominates and sweeps them away. Another possibility involves cohesion. If dust particles are sticky, perhaps coated with organics, perhaps electrostatically charged, they might clump together immediately upon release, forming aggregates too heavy to escape. This would suppress tail formation, while still allowing gas to escape freely, creating exactly the observed situation. Active coma, absent tail. Cohesive dust has been observed on other comets, particularly those with organic-rich compositions, so this mechanism has precedent. A third possibility involves viewing geometry. If the dust tail points directly toward or away from Earth, it would appear foreshortened to invisibility, hidden along the line of sight. This explanation is geometrically plausible, but statistically unlikely. Orbital mechanics makes it rare for tail, sun, and observer to align precisely. Moreover, multiple observatories at different viewing angles have failed to detect the tail, suggesting it's not merely hidden by geometry, but genuinely weak or absent. The rotation complicates everything. As the nucleus spins, different regions rotate into sunlight, each with potentially different compositions, different sublimation rates, different dust entrainment efficiencies. If only certain regions produce dust, and those regions happen to be oriented such that ejected dust doesn't align with the anti-solar direction, you could suppress tail formation even with ongoing activity. This requires specific but not impossible configurations of rotation axis, jet locations, and observing geometry. Historical parallels exist but don't fully satisfy. 2I Borisov, the previous interstellar comet, developed a magnificent tail visible in amateur telescopes, proving that interstellar objects can behave conventionally. Oumuamua showed no tail despite passing much closer to the Sun than 3I Atlas, sparking the controversies that Loeb and others continue to debate. 3I Atlas occupies a middle ground, more active than Oumuamua, less spectacular than Borisov, but that middle ground feels uncomfortable, like an average that hides extremes rather than representing typical behaviour. The public hook here is visceral. A comet that spins like clockwork, vents gas into space, sheds dust into its coma, yet refuses to grow a tail. How is that possible? It's like watching a car with its engine running, wheels spinning, but going nowhere because the transmission is stuck in neutral. All the components are present and functioning, but the expected outcome, forward motion, or in this case, tail formation, never materializes. The disconnect between activity and visible consequence creates cognitive dissonance that no amount of technical explanation fully resolves. Speculation about engineered suppression is tempting but unsupported. Could an artificial object intentionally minimize its reflective signature, outgassing just enough to match comet expectations but avoiding the bright tail that would make it conspicuous? Technically yes, but why? What advantage would invisibility confer to a probe visiting our solar system? Unless detection itself is dangerous, perhaps civilizations avoid contact, perhaps interstellar law prohibits obvious intrusions, there's no clear motive for stealth. And even if motive existed, the execution seems imperfect, since we detected 3I Atlas anyway and are scrutinizing its every anomaly. The natural explanation remains favoured by most researchers. Unusual but permitted grain properties combined with modest activity rates produce a coma without a tail. This interpretation requires no new physics, invokes no exotic materials or intelligence, and fits within the broad envelope of cometary diversity we've observed in solar system objects. The fact that it feels unsatisfying, that it leaves nagging questions about why the grains would have these particular properties, doesn't invalidate it. Nature isn't obligated to satisfy our aesthetic preferences for elegant explanations, yet the anticipation builds as 3I Atlas approaches perihelion, that point of closest approach to the Sun where solar heating maximizes and activity should peak. If the tail is going to appear, it will be then. JUICE observations, coordinated ground campaigns and space telescopes will all watch for the moment when sublimation crosses some threshold and the missing tail suddenly manifests, streaming behind the nucleus like a banner unfurling. That moment, if it comes, will resolve much of the mystery, and if it doesn't come, if 3I Atlas passes perihelion still tailless despite maximum heating, the anomaly will crystallize into something demanding more creative explanations than unusual dust or unlucky viewing angles. The next few weeks will tell us whether 3I Atlas is merely an oddball within natural bounds, or something genuinely outside our framework for understanding cosmic debris. Part 8. Extreme negative polarization. What it suggests. Light is a wave, oscillating electromagnetic fields propagating through space at 300,000 kilometers per second. Normally, light from the Sun is unpolarized. Its oscillations occur randomly in all perpendicular planes to the propagation direction, creating no preferred orientation. But when light scatters off particles, dust grains, atmospheric molecules, comet debris, it can become polarized, with oscillations preferentially aligned in one direction. Measuring this polarization reveals information about the scattering particles that other techniques can't access, making polarimetry a powerful diagnostic in astronomy. For 3I Atlas, polarimetric observations revealed something unusual. The degree of linear polarization, what fraction of light becomes polarized after scattering, showed a deep negative branch at small phase angles. Phase angle is the Sun-comet observer angle, essentially measuring from what angle you're viewing reflected sunlight. At phase angles around 17 degrees, 3I Atlas's polarization reached minus 2.7%, meaning light became polarized perpendicular to the scattering plane rather than parallel to it. This negative polarization is common at small phase angles for many solar system bodies, but the depth matters. Most comets show negative branches around minus 1 to minus 1.5%. A few outliers reach minus 2%. 3I Atlas's minus 2.7% places it at the extreme end of observed values, suggesting dust properties significantly different from the norm. The inversion angle, where polarization switches from negative to positive as phase angle increases, occurred around 17 to 18 degrees. also slightly unusual compared to typical comets which invert around 20 to 25 degrees. What does this mean physically? Polarization theory is complex, involving me-scattering calculations for spherical particles, more complicated models for irregular shapes, and interactions between electromagnetic waves and material optical properties. But the general principle is that negative polarization at small phase angles arises from multiple scattering events and coherent backscattering effects, where light scatters multiple times within porous aggregates before escaping. The deeper the negative branch, the more efficient this process, which typically correlates with highly porous fluffy dust grains, particles that are more void than solid, with fractal structures where tiny subparticles cling together in loose arrangements. Laboratory measurements of cometary analog materials help interpret these observations. Researchers create synthetic dust, mixtures of silicates, organics, ices, and measure their polarization properties under controlled conditions. Porous aggregates with porosity exceeding 90%, meaning 90% voids, 10% solid, produce deep negative branches similar to what 3I Atlas exhibits. These structures are fragile, easily disrupted by collisions or compressive forces, but can persist in the gentle environment of space where velocities are low and collisions rare. Alternative interpretations invoke unusual compositions rather than unusual structures. Certain materials, perhaps carbon-rich organics, perhaps specific silicate mixtures, scatter light with polarization properties differing from typical silicates found in solar system dust. If 3I Atlas's dust is chemically exotic, reflecting its interstellar heritage and formation in a thick disk environment with different elemental abundances, the polarization anomaly could arise from composition rather than porosity. There's also the possibility of surface coatings. Dust grains might be core mantle structures, silicate cores coated with organic mantles, or vice versa, where the mantle dominates light scattering properties. Such structures could produce unusual polarization without requiring extreme porosity or bulk composition changes. Coatings are common in solar system dust, formed when gases condense onto cold grain surfaces or when energetic processing alters surface layers. Connecting polarization to the missing tail requires some theoretical gymnastics, but pathways exist. If dust grains are unusually porous and fluffy, they might have low terminal velocities in the coma. They drift slowly away from the nucleus rather than being rapidly accelerated by gas drag. This would create a compact coma where dust lingers near the nucleus, rather than streaming away into a tail. Additionally, fluffy aggregates might be susceptible to disruption by solar radiation pressure or electrostatic forces, fragmenting into smaller subparticles that scatter light less efficiently, rendering the tail optically faint even if physically present. Speculation about artificial materials is inevitable but poorly constrained. Could engineered dust produce extreme negative polarization? Hypothetically, yes. Carbon nanotubes, graphene sheets, metamaterials with designed optical properties, these could scatter light in unusual ways. But invoking such materials requires explaining why an artificial object would bother mimicking natural dust polarization at all, why it would choose this specific scattering behavior, and what purpose such mimicry serves. The speculation lacks motive and mechanism, making it entertaining but scientifically unproductive without supporting evidence. The polarimetric data does contribute to Loeb's constellation of anomalies. It's another measurement that places 3I Atlas at the statistical edge of cometary behavior, another data point suggesting this object is unusual even within the diverse population of comets we've studied. Whether that unusualness reflects natural diversity after all, interstellar objects sample different formation environments and might systematically differ from solar system comets, or something more exotic remains contested. Some researchers caution against overinterpreting single measurements. Polarimetry is challenging, requiring careful calibration, precise knowledge of instrumental systematics, and corrections for atmospheric effects that can introduce spurious polarization. The observations of 3I Atlas were conducted at the limit of feasibility given the object's faintness, and error bars on the polarization measurements, while reported, might underestimate systematic uncertainties. Perhaps more data with better signal-to-noise would show less extreme values, bringing 3I Atlas back within normal bounds, but the measurements stand as reported, and multiple independent observations show consistent results, suggesting the deep negative branch is real rather than artifact. If real, it demands explanation, either through porous dust structures, exotic compositions, or mechanisms we haven't fully considered. The coming observations, particularly from JUICE with its polarimetric capabilities, might refine these measurements, confirming or refuting the extreme values and helping to distinguish between competing interpretations. The dust question becomes central to understanding 3I Atlas's nature. Is this object simply a comet with unusual grain properties arising from its interstellar heritage? Or is the dust itself a clue pointing toward deeper mysteries, perhaps ancient materials from the thick disk, perhaps organic-rich aggregates carrying prebiotic chemistry, perhaps something we haven't imagined because our reference frame is limited to solar system experience? Polarimetry hints at answers but delivers ambiguity, adding texture to the mystery without resolving it. Like a crossword clue that fits multiple words equally well, forcing you to seek additional constraints before filling in the blank with confidence. Part 9. Alternate hypotheses, exotic theories. Every anomaly admits multiple explanations, and 3I Atlas has accumulated enough anomalies to support an entire taxonomy of hypotheses ranging from mundane to exotic. The scientific method demands we exhaust natural explanations before invoking extraordinary ones. So let's catalogue the conventional possibilities first, then venture cautiously into more provocative territory. The most straightforward natural explanation for the missing tail involves viewing geometry. If the tail points directly toward or away from Earth, aligned with our line of sight, it becomes invisible through foreshortening, compressed into a point rather than extending across our field of view. This explanation is geometrically plausible and requires no unusual physics, but it faces challenges. Multiple observatories at different locations observing over weeks should provide varied viewing angles, yet none detected clear tail extension. The geometry would need to be conspiratorially aligned across multiple observation epochs, which strains statistical credibility. A second natural explanation invokes low dust production. If 3I Atlas produces gas but minimal dust, perhaps because its composition lacks fine-grained material, perhaps because surface crusts prevent dust entrainment, the tail would be dominated by ions rather than dust. Ion tails are fainter, visible primarily in ultraviolet wavelengths, where ionized molecules emit, and easily missed in visible light observations. This fits the spectroscopic data showing gas presence, and the imaging data showing no visible tail. But it doesn't fully explain why dust production is so suppressed compared to gas, especially for an object actively outgassing carbon dioxide. A third explanation emphasizes unusual dust properties, large grains, high porosity, or sticky aggregates that fall back to the nucleus rather than escaping into the tail. We've discussed this already, but it bears repeating as the favoured hypothesis among most researchers. It requires no exotic physics, fits within observed cometary diversity, and aligns with the polarimetric evidence for fluffy grains. The missing tail becomes a consequence of dust dynamics, rather than sublimation absence. Carbon dioxide dominance offers another angle. Water sublimation entrains dust efficiently, because water's latent heat of sublimation is large, driving vigorous gas flows that drag dust along. Carbon dioxide sublimation is less energetic per molecule, producing weaker gas flows that might lift dust less efficiently. If 3I Atlas is predominantly carbon dioxide ice with minimal water, dust entrainment could be suppressed even with substantial sublimation, creating gas-rich but dust-poor emissions. Particle absorption provides a fifth possibility. If dust grains are exceptionally dark, perhaps carbon-black organics, perhaps iron-rich silicates, they'd scatter little sunlight even if present in substantial quantities. The tail would exist physically, but remain optically invisible, hidden because it reflects insufficient light to stand out against background sky. This explanation struggles with observations that do detect coma dust, suggesting grains aren't entirely non-reflective, but perhaps the coma dust differs from tail dust in size or composition. Exotic hypotheses begin where natural explanations struggle. The least exotic explanation is that 3I Atlas represents a transitional object, neither fully comet nor fully asteroid, perhaps a fragment of a larger body that was partially processed by internal heat or collisional disruption, leaving it with unusual volatile distributions and dust properties. Such objects might exist in solar system populations too, occupying the blurred boundary between comets and asteroids where classification becomes ambiguous. More provocative is the artificial structure hypothesis. If 3i Atlas were a manufactured object, a probe, a derelict spacecraft, a light sail fragment, it might outgas from residual volatiles accumulated over millions of years of interstellar travel without producing the dust-rich tail natural comets generate. An engineered surface might minimize dust production deliberately to avoid contamination of instruments, or to reduce radar cross-section for stealth purposes. The carbon dioxide dominance could reflect intentional choice of propellant or accidental accumulation of interstellar carbon dioxide ice on external surfaces. This hypothesis faces immediate objections. Where are the signs of geometric regularity? Artificial structures tend towards straight edges, right angles, modular construction, features we don't observe in 3i. Atlas's unresolved images. Where are the material signatures? Metals, polymers, composites should produce distinct spectroscopic or polarimetric features different from rock and ice, yet observations show compositions broadly consistent with natural minerals and organics. Where are the anomalous dynamics? Artificial objects might exhibit controlled attitude changes, propulsive maneuvers, or electromagnetic emissions, none detected. Loeb's light sail hypothesis, applied originally to Oumuamua and now echoed for 3i Atlas, proposes a thin reflective surface accelerated by solar radiation pressure. The forward acceleration noted in astrometric data could arise from radiation pressure if the object is flat and oriented appropriately. The missing tail follows naturally. Sails don't produce tails unless coated with volatiles that sublimate, and even then tail formation would differ from cometary norms. The carbon dioxide detection might come from ice accumulated on the sail during interstellar travel, now sublimating as solar heating increases. But the light sail hypothesis struggles with spin. Sails under radiation pressure would experience torques that spin them up rapidly, unless they're perfectly symmetric or use active stabilization. 3i Atlas's 16-hour rotation suggests no such stabilization, pointing toward a natural irregular body tumbling under angular momentum conservation. Additionally, the coma's spherical symmetry contradicts what you'd expect from a sail, which should show asymmetric outgassing from one face, preferentially heated by the sun. Another exotic possibility is a dormant comet undergoing reactivation. Perhaps 3i Atlas spent millions of years in interstellar space with its surface volatiles depleted by cosmic ray processing, forming a crust that prevents sublimation. Upon entering the inner solar system, solar heating slowly breaks through this crust, allowing gas escape but not yet vigorous enough for dust production. The tail might appear later as activity ramps up, meaning we're witnessing an object in transition between dormancy and full activity. The panspermia angle deserves mention. If 3i Atlas originated in a system hosting life, could it carry biological material, spores, dormant microbes, organic molecules synthesized by living processes? The unusual organic signatures suggested by spectroscopy could hint at biological origins, though distinguishing biotic from abiotic organics remotely is nearly impossible. Panspermia advocates note that life spreading between stars via ejected comets is thermodynamically plausible. A small fraction of ejected material eventually lands on habitable planets, and some organisms might survive the journey frozen in ice. 3i Atlas becomes a potential carrier, a biological ambassador from another world. This is speculation layered on speculation. We don't know if the organics are unusual. We don't know if they're biotic. We have no capability to test for biosignatures remotely with current instruments. But the idea tantalizes because it transforms 3i Atlas from mere curiosity into potentially the most important scientific discovery in human history, direct evidence of extraterrestrial life, even if only microbial, even if long dead, delivered to our solar system by natural processes. Pop culture parallels are inevitable. Arthur C. Clarke's Rama, a cylindrical alien artifact that enters the solar system disguised as an asteroid, captured imaginations decades ago. The Black Knight satellite myth, a supposed artificial object in Earth orbit, persists despite debunking. Every unusual astronomical observation gets filtered through these narratives, cultural templates for interpreting anomaly as artificiality. 3i Atlas fits the pattern, mysterious, anomalous, resistant to easy explanation, making it a perfect screen onto which we project hopes, fears, and sci-fi influenced expectations. The key question cutting through speculation is, why is ESA treating this so urgently? The JUICE retasking, the public announcements emphasising unexpectedness, the rapid publication of initial results all suggest institutional recognition that 3i Atlas is scientifically important beyond routine comet observation. Does ESA know something not yet public? Have internal analyses revealed additional anomalies that haven't appeared in published papers? Or is the urgency simply prudent response to a rare opportunity, recognising that interstellar visitors don't wait for bureaucratic schedules and must be observed while accessible? Transparency in science argues against hidden bombshells. Major discoveries typically leak through conference presentations, preprints, informal discussions before official publication. If ESA had detected clear evidence of artificiality, geometric structures, radio signals, impossible materials, someone would have talked, and internet rumours would propagate faster than official announcements. The absence of such rumours suggests no smoking gun exists, just accumulating circumstantial strangeness that collectively warrants attention without individually proving anything definitive. The epistemological challenge is recognising when anomalies stop being noise and start being signal. One anomaly is curiosity. 2 might be coincidence. 3 raises eyebrows. 4 or 5 in the same object begins to feel like a pattern. 3i Atlas has assembled a collection: missing tail, carbon dioxide dominance, unusual polarization, forward acceleration, red dust slope, that individually admit natural explanations but collectively create unease. At what point does unusual but natural become, we need to seriously consider alternatives? Science doesn't have a fixed threshold, only a cultural tendency toward conservatism that resists exotic explanations until absolutely forced by data. That forcing hasn't happened yet with 3i Atlas, and may never happen. The coming observations could resolve everything naturally, showing tail formation at perihelion, confirming grain properties explain polarization, demonstrating that carbon dioxide comets from the thick disk simply behave differently than we expected. The mystery would fade, replaced by deeper understanding of cometary diversity and interstellar object properties. Science would advance incrementally, another data point added to the catalogue, another lesson learned about nature's inventiveness. Or the anomalies might persist, resistant to natural resolution, demanding we expand our framework for understanding cosmic debris to include possibilities we've barely considered. That expansion wouldn't necessarily mean aliens. It could mean new physics of dust aggregation, unexpected chemical pathways in ancient stellar environments, dynamics we haven't modelled because we've never encountered the right conditions. But it would mean acknowledging that our current models, built on solar system experience, might be incomplete or even misleading when applied to objects from beyond. And in that acknowledgement lies the real value of interstellar visitors, not as potential artifacts, but as teachers, forcing us to confront the limits of our knowledge and expand our understanding to encompass the broader galaxy's diversity. The question isn't whether 3i Atlas is natural or artificial. The question is whether we're intellectually flexible enough to recognise new categories of natural when they arrive, or whether we'll remain trapped in false dichotomies that limit rather than liberate our thinking. Part 10. Hidden angles, tensions and red flags. Science rarely proceeds smoothly from observation to understanding. More often, the path winds through contradictions, ambiguous measurements, and debates where reasonable people interpret identical data differently. 3i Atlas embodies this messy reality, presenting a tangle of measurements that refuse to cohere into a simple narrative. Let's examine the specific tensions that make this object so frustrating and fascinating in equal measure. First, there's the brightness cross-section problem. Early estimates based on apparent magnitude and distance suggested 3i Atlas's nucleus might be several kilometres across, large enough to be gravitationally significant, massive enough to retain substantial volatiles. But the ExoMars image showed an unresolved nucleus, meaning it could be much smaller than those estimates, perhaps only hundreds of metres in diameter. How do we reconcile bright apparent magnitude with potentially small size? Either the albedo is much higher than typical comets, reflecting more sunlight per unit area, or the coma contributes more to total brightness than expected, or our initial size estimates were simply wrong due to uncertain assumptions about dust scattering efficiency. This matters because size determines mass determines gravitational binding energy, and Binding energy determines whether outgassing can significantly alter the object's trajectory. Small objects experience larger accelerations from the same outgassing rates compared to large objects. If 3I Atlas is small, the non-gravitational accelerations Loeb noted become easier to explain naturally. If it's large, those accelerations require more vigorous or asymmetric outgassing to produce the observed trajectory changes. Second, there's tension in the acceleration measurements themselves. Different researchers analysing the same astrometric data reach different conclusions about the magnitude and direction of non-gravitational forces. Some find forward acceleration consistent with Loeb's claims. Others find accelerations perpendicular to the sunline, consistent with typical cometary jetting. Still others argue that measurement uncertainties are large enough that any claimed detections are marginal at best, possibly artifacts of systematic errors in position measurements or background star catalogue positions. This isn't unusual in asteroid and comet astrometry. Measuring tiny accelerations requires exquisite precision, and small systematic errors, atmospheric refraction, telescope tracking imperfections, catalogue mismatches can masquerade as real forces. The debate will resolve only with more observations spanning longer time baselines, allowing trajectory integrations that average out random errors and reveal genuine dynamical behaviour. But for now, uncertainty reigns, and claims of unusual acceleration remain contested. Third, the unresolved nucleus creates fundamental ambiguity. We don't know 3I Atlas's shape, surface properties, rotation axis orientation, or detailed composition. All we see is the coma, that fuzzy envelope that could hide a multitude of nuclear configurations. Is the nucleus elongated like Oumuamua, or roughly spherical? Is it monolithic, or a loose rubble pile held together by weak gravity? Does it have surface features, craters, cliffs, jets, or is it smooth and featureless? These unknowns propagate through every analysis, forcing researchers to make assumptions that might be wildly incorrect. Technical challenges amplify these ambiguities. 3I Atlas is faint, requiring long exposures that accumulate noise and complicate background subtraction. It's moving, requiring tracking that introduces blur or demands sophisticated image stacking. It's distant, resolving details requires the best instruments operated at their limits. Even Hubble and JWST struggle with objects this faint and fast-moving, producing images and spectra with signal-to-noise ratios barely above detection thresholds. There's also selection bias to consider. We're primed by recent history to see anomalies in interstellar objects. Oumuamua's strangeness set expectations that subsequent visitors would also be weird. Every deviation from typical cometary behaviour gets amplified, discussed, debated, while conforming behaviours are noted, briefly and forgotten. This doesn't mean the anomalies are illusory, they're real measurements, but it might mean we're interpreting them through a lens of expectation that magnifies their significance beyond what data alone supports. Red flags accumulate when multiple independent anomalies appear in the same object. In isolation, each can be explained. Carbon dioxide dominance, interstellar heritage, missing tail, geometry or grain size, unusual polarization, porous dust, forward acceleration, asymmetric outgassing, but explaining all of them simultaneously in ways that mutually cohere is harder. You need a model where carbon dioxide dominates, which produces gas flows that don't entrain dust efficiently, which creates porous grains through specific aggregation processes, which align with outgassing patterns that produce forward acceleration. Each step plausible, but the combined scenario feeling increasingly contrived. This is where Bayesian reasoning becomes relevant. In Bayesian analysis, you update probabilities based on accumulating evidence. One anomaly slightly increases the probability of exotic explanations, but not dramatically. Multiple anomalies compound, each one shifting probabilities further. At some point, though, where exactly is subjective, the cumulative weight of evidence makes exotic explanations competitive with conventional ones, not because any single measurement proves the exotic case, but because the conventional explanations have been stretched thin trying to accommodate everything simultaneously. Critics argue this is precisely where bias creeps in. If you start with low prior probability for artificial origin, which most scientists do, given the rarity of technological civilizations in the cosmos, then even multiple anomalies don't shift that probability much. You still favour natural explanations because the prior heavily weights them. Only if you start with higher priors for artificiality or exotic natural processes do the anomalies significantly shift your posterior probabilities toward those alternatives. Public versus scientific tensions exacerbate these debates. Headlines proclaim alien-like comet, or mystery object baffles astronomers, creating impressions of consensus confusion when really there's robust debate within normal scientific bounds. Scientists reading these headlines cringe, seeing their careful caveats and uncertainties transformed into sensationalism. But the public, hungry for cosmic significance and disappointed by years of maybe aliens but probably not stories, latches onto the anomalies as hints that finally, this time, we've found something genuinely strange. ESA's cautious but engaged response walks a middle line. The agency acknowledges unexpectedness, unexpected for everybody, without endorsing exotic explanations. It retasks JUICE, signalling scientific importance, without claiming breakthroughs. It releases images and data promptly, maintaining transparency, without premature conclusions. This professionalism is reassuring but also frustrating for those who want clear answers. Is 3i Atlas weird or merely unusual? Is it worth the fuss, or are we overreacting to measurement noise and selection effects? The open issues multiply as observations continue. Will the tail emerge after perihelion when solar heating maximizes? Will JUICE resolve the nucleus or provide better coma characterization? Will spectroscopy reveal additional chemical surprises? Perhaps isotopic ratios diagnostic of ancient stellar environments? Perhaps molecular species unknown in solar system comets? Will polarimetry refine dust properties, narrowing the range of compositions and structures consistent with observations? Will long-term astrometry settle the acceleration debate, distinguishing real forces from measurement artifacts? Each of these questions could resolve in ways that naturalize 3i Atlas, folding it back into understood categories with perhaps a few footnotes about its unusual but explainable properties. Or they could deepen the mystery, confirming anomalies, adding new ones, pushing the object further from comfortable explanations. Science thrives on this uncertainty, on the productive tension between data and model, observation and theory. But the public, and even some scientists, crave resolution, the satisfaction of knowing, the comfort of categories that fit. What we're witnessing is science in its rawest form, messy, uncertain, contested, honest about what it doesn't know. This is healthier than false confidence, more authentic than premature consensus, but it's uncomfortable, leaving us suspended between possibilities, unable to declare victory for any hypothesis. 3i Atlas teaches patience, humility before complexity, respect for the difficulty of extracting truth from sparse, noisy, ambiguous data collected across millions of kilometers of space. The red flags wave not as warnings of danger, but as markers of frontier territory, regions where our maps are incomplete and our understanding provisional. Exploring that territory requires courage to speculate balanced with discipline to demand evidence, imagination to entertain exotic possibilities, balanced with skepticism that prevents wishful thinking from masquerading as discovery. Part 11. Origin Story. Thick disk, ancient interstellar home. Every object carries within it the story of its birth, encoded in chemistry, structure, and dynamics. For 3i Atlas, that story begins not in our cosmic neighbourhood, but in the ancient reaches of the Milky Way's thick disk, a population of stars formed when the galaxy was young and the universe less enriched with heavy elements. Recent orbital modelling work, integrating 3i Atlas's trajectory backward through millions of years of galactic dynamics, suggests this unexpected origin, not from the thin disk where our sun resides, but from the puffed-up halo of older stars orbiting above and below the galactic plane. The thick disk formed 8 to 12 billion years ago, during an epoch when the Milky Way was smaller, more chaotic and chemically different from today. Stars in the thick disk show lower metallicities, fewer heavy elements like carbon, oxygen, silicon, iron, because the interstellar medium from which they condensed hadn't been enriched by as many supernova explosions. These stars orbit the galactic centre with higher velocities perpendicular to the disk plane, their orbits tilted and eccentric, reflecting the violent processes that formed the thick disk. Perhaps galactic mergers, perhaps intense star formation in the early galaxy's turbulent youth. If 3i Atlas originated from a planetary system around a thick disk star, its chemistry suddenly makes more sense. Low metallicity environments produce different mineral condensation sequences in protoplanetary disks. Carbon to oxygen ratios shift, affecting whether carbon locks into carbon monoxide, carbon dioxide, or organic molecules versus being trapped in silicates or graphite. Water ice abundance might be lower if oxygen is scarce or preferentially bound in other forms. The carbon dioxide dominance we observe could be a direct signature of formation in a low metallicity, carbon-rich environment, unlike the solar system's metal-rich natal nebula. The backward trajectory integration required to identify 3I Atlas's origin is computationally intensive and fraught with uncertainties. You start with its current position and velocity, measured from astrometric observations, and integrate the equations of motion backward in time, accounting for gravitational forces from the Sun, planets, nearby stars, the galactic disk, the bulge, dark matter halo, every significant mass that could perturb the trajectory. Over millions of years, small uncertainties in initial conditions and gravitational potential accumulate, creating a probability cloud rather than a single trajectory. That cloud expands as you go further back, eventually encompassing multiple possible origin regions. Despite uncertainties, the modelling consistently points toward the thick disk rather than the thin disk or halo populations. The object's current velocity vector, its orbital inclination relative to the galactic plane, and its energy all argue for thick disk origin. This doesn't pinpoint the specific star system. Too much time has elapsed, too many dynamical interactions have occurred, but it narrows the possibilities to stars of certain ages, metallicities, and kinematic families. This result elevates 3I Atlas from interesting to precious. Objects from the thick disk are rare visitors to the inner solar system. Most interstellar objects likely come from thin disk stars like our Sun, young systems with metal-rich compositions similar to ours. Thick disk objects offer a window into galactic history, into chemical conditions prevailing billions of years before the Sun, formed into the diversity of planetary systems that arose when the galaxy was fundamentally different from its current state. Could this explain the unusual composition? Almost certainly, at least partially. Comets forming around metal-poor stars would incorporate different ice mixtures, different dust compositions, different organic inventories than solar system comets. The carbon dioxide dominance, the red dust slope, perhaps even the unusual polarization, all could reflect formation chemistry shaped by a parent star's elemental abundances. Laboratory studies of meteorites from metal-poor environments, if we had any, which we don't, would show similar deviations from solar system norms. There's also the question of age. If 3I Atlas is 8 to 12 billion years old, formed shortly after its parent star, it's been wandering the galaxy for epochs that dwarf our solar system's 4.6 billion year age. During that immense span, the object has been bombarded by cosmic rays, exposed to ultraviolet radiation from passing stars, impacted by interstellar dust grains, and thermally cycled through variations in ambient radiation fields. These processes alter surface chemistry, creating organic residues, amorphizing crystal structures, and driving volatile loss from outer layers. An ancient object might behave differently than a young one. Volatile ices could be depleted from the surface layers, creating crusts that inhibit sublimation until solar heating breaks through. Dust grains might be more processed, their structures altered by radiation damage, their surfaces coated with organic tars produced by photochemical reactions. The unusual polarization could partly reflect billions of years of weathering that no solar system comet has experienced, simply because solar system objects are much younger. Speculation about ancient probes inevitably arises when discussing thick disk origins. If technological civilizations exist, some must have arisen in the thick disk's ancient stellar populations, potentially billions of years before Earth formed. An 8-billion-year-old civilization would have had time to spread across the galaxy, send probes to countless systems, perhaps even die out, leaving only their artifacts drifting through space. 3I Atlas, if it was such an artifact, would be a derelict relic, its systems long dead, its mission forgotten, its makers extinct. We'd be examining archaeological material from a civilization older than our planet. This is deep speculation, unsupported by evidence, but it illustrates how origin stories shift context. An object from the thick disk carries weight beyond its physical properties. It's a time traveller, a messenger from the deep past. potentially a sample of conditions and processes we can study nowhere else. Even if entirely natural, it's scientifically invaluable, worth every effort to characterise because the information it contains can't be obtained through any other means, short of interstellar travel to visit thick disk stars directly. Historical context from panspermia theories adds another dimension. If life arose early in galactic history, perhaps facilitated by older, metal-poor stars that nonetheless had suitable planets, then comets and asteroids ejected from those ancient systems could have seeded younger systems with organic molecules, amino acids, perhaps even viable microorganisms. Panspermia doesn't require intentional seeding. Natural ejection processes suffice. But if 3I Atlas originated from a thick disk system that hosted life, it might carry chemical or biological signatures that reveal extraterrestrial biology's existence, distribution, and antiquity. Detecting such signatures remotely is nearly impossible with current technology. We'd need returned samples analysed in Earth laboratories with techniques sensitive enough to distinguish biological from abiotic organics, sterile from contaminated materials, ancient from recent deposits. But the possibility tantalises, transforming 3I Atlas from cosmic debris into potential Rosetta Stone for astrobiology, a key to understanding whether life is common in the galaxy, whether it spreads between stars, whether we're alone or part of a much larger biological community. The thick disk origin also implies that interstellar objects are more diverse than our small sample suggests. If visitors come from different stellar populations, thin disk, thick disk, halo, perhaps even extragalactic objects from satellite dwarf galaxies merging with the Milky Way, then each visitor samples different formation environments, chemical abundances, and evolutionary histories. Oumuamua, 2I Borisov, and 3I Atlas might represent distinct categories rather than variations on a common theme. Characterizing that diversity requires many more detections, better statistics, and improved understanding of how galactic dynamics deliver objects from different populations into the inner solar system. Looking ahead, the thick disk origin hypothesis makes testable predictions. If correct, 3I Atlas's isotopic ratios should differ from solar system values, showing signatures of nucleosynthesis in metal-poor stars. Its organic molecules, if any are identified, might show unusual compositions reflecting different synthetic pathways. Its dust mineralogy might include phases rare in solar system materials but expected from low metallicity condensation. Each of these predictions can be tested with improved spectroscopy, polarimetry, and eventually, if we're ambitious and fortunate, sample return missions that intercept interstellar objects and bring back physical material for laboratory study. That future remains distant but conceivable. Technology is advancing, survey capabilities improving, and interest in interstellar objects growing. Within decades, we might routinely detect dozens of visitors per year, characterize them in detail, perhaps even send rapid response spacecraft to rendezvous with particularly interesting targets. 3I Atlas, in that context, becomes a pioneer, the object that forced us to think seriously about galactic origins, ancient chemistry, and the possibility that every interstellar visitor is unique, carrying stories from corners of the galaxy we'll never visit, but can study through the messengers that occasionally wander our way. Part 12. 3I Atlas's place among interstellar visitors. 3 confirmed interstellar objects in 8 years of intensive searching establishes a detection rate but doesn't yet define a population. Each visitor has been radically different from the others, suggesting that interstellar space contains enormous diversity, or that our sample is too small to reveal underlying patterns. Let's compare 3I Atlas with its predecessors to understand what it adds to our emerging picture of the galaxy's wandering debris. Oumuamua arrived first, detected on October 19, 2017, by Pan-STARRS telescope in Hawaii. The name, Hawaiian for scout or messenger, proved apt. It was indeed the first confirmed interstellar visitor, though retrospective searches found no pre-covery images despite its passage through well-surveyed regions of sky. Oumuamua's most striking feature was its extreme elongation, inferred from brightness variations suggesting axis ratios around 10:1, cigar-shaped or possibly pancake-shaped depending on assumptions about rotation. It showed no visible coma or tail despite passing within 0.25 AU of the Sun, well inside Mercury's orbit where any ice should vaporize vigorously. Yet, Oumuamua exhibited non-gravitational acceleration away from the Sun, suggesting some form of outgassing despite no visible coma. This paradox sparked intense debate. Natural explanations invoked hydrogen ice, nitrogen icebergs, or extremely weak sublimation producing gas but no dust. Exotic explanations, championed by Loeb, suggested artificial origin, perhaps a light sail pushed by solar radiation pressure. The debate remains unresolved, with most astronomers favouring natural explanations while acknowledging that Oumuamua was genuinely strange. 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, behaved conventionally. It displayed a clear coma and tail spectroscopy showing water vapour, carbon monoxide and typical cometary volatiles. Its composition was notable for high carbon monoxide abundance, suggesting formation in cold outer regions of its parent system, but nothing outright anomalous. Polarimetry showed normal values, dust production rates fit expectations, and non-gravitational forces aligned with standard cometary outgassing models. Borisov was the interstellar comet everyone expected, reassuring evidence that not all visitors are weird, that familiar physics operates in other star systems too. Now 3I Atlas arrives. Hybrid. In character, more active than Oumuamua, less spectacular than Borisov, occupying uncomfortable middle ground. It has a coma, confirming activity, but no visible tail, suggesting suppressed dust production. Its composition is unusual but not impossible, carbon dioxide dominating in ratios unexpected for solar system comets, but plausibly explained by interstellar heritage. Its polarization is extreme, but within natural bounds if you allow for unusual dust structures. Its dynamics show possible non-gravitational forces, though measurements remain contested. What patterns emerge from comparing these three? First, diversity is real. Interstellar visitors don't conform to a single template. They vary in size, shape, composition, activity level and behaviour, just like solar system comets and asteroids vary enormously, despite sharing common origins. This suggests that planet formation and ejection processes operate similarly across the galaxy, but with enough parameter variation, stellar mass, metallicity, disk temperature profiles, giant planet configurations, to produce wide ranges of outcomes. Second, anomalies might be common. 2 of 3 interstellar visitors showed behaviour surprising enough to generate scientific controversy. Oumuamua with its acceleration and lack of tail, 3I Atlas with its tailless activity and unusual composition. If this ratio holds, most interstellar objects will challenge expectations in some way, either because they truly differ from solar system analogues, or because our detection biases favour unusual objects that appear bright or behave oddly, making them easier to spot and study. Third, our understanding remains provisional. Each new visitor forces theoretical updates, models adjusted, assumptions questioned, new mechanisms invoked. This is healthy scientific progress, evidence that the field is alive and responsive to data rather than ossified into dogma. But it also reveals how little we actually know about interstellar object populations. Are most like Borisov, with Oumuamua and 3I Atlas being outliers? Or is Borisov the outlier, and strangeness is typical? We can't answer with 3 data points. Detection improvements promise rapid expansion of the sample. The Vera Rubin Observatory, when fully operational, will detect tens to hundreds of interstellar objects per year, building statistical samples large enough to identify true patterns versus random variations. Within a decade, we'll know whether carbon dioxide dominance is common in interstellar comets from certain environments, whether most objects show weak tails, whether non-gravitational forces typically align with solar heating or suggest other processes. The uncertainty will narrow, replaced by knowledge built on robust statistics. Speculative possibilities persist around the idea of engineered objects. If even a tiny fraction of interstellar objects are artificial, discarded probes, light sail fragments, technological debris, then increased, detection rates might reveal them through statistical anomalies. Perhaps certain size ranges are suspiciously overpopulated. Perhaps trajectories show non-random clustering toward ecliptic or planetary orbits. Perhaps spectroscopic signatures reveal materials impossible to form naturally. These signals would be subtle, requiring large samples to detect, but they'd be definitive if found. Alternatively, every object might be natural, with apparent anomalies arising from observational biases, measurement limitations, and insufficient theoretical models. We might look back in 20 years and laugh at how primitive our understanding was in 2025, how we mistook ignorance for mystery, how we speculated about aliens when we simply hadn't figured out the physics of porous dust aggregates in low metallicity ices. This humility is important. Science advances by recognizing its limitations, not by clinging to mysteries when explanations emerge. The comparison also highlights what we're missing. We have images but no close-up photographs. We have spectra but no mass spectrometry of actual samples. We have dynamics but no direct measurements of outgassing patterns or surface properties. Every interstellar visitor has been studied from millions of kilometres away, observed through telescopes struggling at the limits of sensitivity, characterised through indirect inference rather than direct examination. The next revolution in interstellar object science will come from proximity, spacecraft launched to intercept visitors, perhaps even sample return missions that bring material back to Earth for laboratory analysis. Such missions face enormous technical challenges. Interstellar objects move fast and are detected late, leaving little time to launch intercept trajectories. They're distant when discovered, requiring years of travel time to reach even if we launch immediately. They're unpredictable in size and danger. Rendezvous with an actively outgassing comet risks spacecraft damage from dust impacts or gas jets. But the scientific payoff would be transformative, turning vague remote sensing hints into concrete physical and chemical data that settles current debates definitively. For now, 3i Atlas joins the catalogue as the third confirmed member, a strange but possibly not anomalous representative of the galaxy's drifting population. It teaches us that interstellar space is filled with remnants of planet formation from across the galaxy's history, that these objects sample chemical and physical conditions we can access no other way, and that every visitor is a gift, free samples delivered to our doorstep, requiring only that we pay attention and study them before they disappear back into the darkness from which they came. Whether 3i Atlas is the most interesting of the three, or just the most recent, time and further observations will reveal. But its place in the sequence is secure, a stepping stone in humanity's gradual expansion of awareness from our solar system to the broader galactic community of wandering objects that connect all stars through the slow exchange of debris across light years and eons. Part 13. Other recent astronomy headlines. The universe refuses to cooperate with our preference for single-topic focus. While 3i Atlas commands attention, other astronomical discoveries unfold simultaneously, each carrying implications that ripple through our understanding of cosmos, life, and humanity's place in it all. Let's briefly survey the broader context of recent months, noting how these parallel stories amplify or illuminate the themes emerging from our interstellar visitor. In late September 2025, James Webb Space Telescope published spectroscopic observations of K2-18b, a mini-Neptune exoplanet orbiting a red dwarf star 120 light-years away. The spectra showed methane and carbon dioxide in the planet's atmosphere, expected for a hydrogen-rich world, but also hints of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by biological processes, particularly marine phytoplankton. The detection remains tentative, requiring confirmation from additional observations, but if real, it would mark the first potential biosignature detected on an exoplanet, transforming the search for life from theoretical exercise to concrete observation. The parallels to 3i Atlas are subtle but real. Both involve interpreting ambiguous data, distinguishing genuine signals from noise and systematic effects, and navigating the tension between extraordinary claims requiring extraordinary evidence and the need to report tentative results before certainty arrives. The dimethyl sulfide detection could be artifact, contamination, or misidentification, just as 3i Atlas's anomalies could be measurement errors or incomplete models. Yet both warrant attention because the potential implications, life on another world, artificial objects in our solar system, are profound enough to justify scrutiny even when probabilities remain low. In early October, a massive coronal mass ejection from the Sun narrowly missed Earth. Passing through orbital space, Earth had occupied just hours earlier. The solar storm was classified as X5 level, powerful enough to disrupt satellites, damage electrical grids, and create auroras visible at mid-latitudes. Earth's miss was luck, not prediction, reminding us that cosmic hazards arrive unannounced and our monitoring capabilities, while improved, remain imperfect. Forecasting solar activity is challenging, and predicting precise trajectories of ejected plasma even more so. This connects to 3i Atlas through the theme of cosmic surprise. We imagine astronomy as predictive, controlled, equations yielding certain forecasts, but reality is messier. Solar eruptions surprise us, interstellar visitors appear unexpectedly, and our models constantly require revision as data contradicts expectations. The universe is under no obligation to behave predictably, and humility before its complexity serves better than confidence in incomplete models. Another headline involves discoveries from the Euclid Space Telescope, launched in 2023 to map dark matter and dark energy across billions of light-years. Early data releases showed galaxy distributions exhibiting unexpected large-scale structures, voids and filaments more pronounced than simulations predicted, suggesting either our cosmological models require adjustment or the observations are revealing details previous surveys missed. The debate is ongoing, with theorists scrambling to explain or dismiss the anomalies depending on their priors about how well we understand the universe's fundamental structure. Again, the parallel to 3i Atlas is thematic. Astronomy repeatedly encounters data that doesn't quite fit, observations that challenge existing frameworks, measurements that force us to question whether anomalies are real signals requiring new physics or artifacts requiring better understanding of systematics. The field advances through this tension, navigating between open-mindedness that allows discovery and skepticism that prevents false claims from derailing progress. These headlines also serve a pedagogical function. They remind us that weirdness is routine in astronomy. Every week brings surprises, black holes behaving unexpectedly, galaxies in places they shouldn't be, stellar explosions that don't match models, exoplanets with bizarre properties. The fact that 3i Atlas is unusual doesn't make it uniquely problematic. Unusual is astronomy's baseline state. What varies is whether unusual means we need better data, or we need better theories, or very rarely, we need radically new paradigms. Public perception conflates these categories, treating every headline as potential paradigm shift. Science communicators struggle with this conflation, trying to convey that most anomalies resolve into mundane corrections, better calibrations, refined models, additional observations filling gaps, without squelching legitimate excitement when rare paradigm shifts do occur. The exoplanet biosignature, if confirmed, would shift paradigms. The Euclid structures will likely refine rather than overturn cosmology. 3i Atlas sits somewhere between, potentially transformative if its anomalies resist natural explanation, likely just interesting if they resolve conventionally. There's also the question of how discoveries interact. If dimethyl sulfide proves real on K2-18b, does that increase or decrease the probability that 3i Atlas is artificial? Some argue it increases. If life is common enough to detect biosignatures on nearby exoplanets, then technological civilizations might be correspondingly common, making artificial interstellar objects more plausible. Others argue it decreases. If life is common, natural organic molecules are ubiquitous, and detecting organics on 3i Atlas says nothing about artificiality. Both arguments are speculative and poorly constrained by data. We don't know if biosignatures correlate with technological development, whether intelligent species commonly produce interstellar probes, or whether detectable artifacts exist in sufficient numbers to be encountered by random chance. The reasoning is too uncertain to yield confident conclusions, serving more as intellectual exercise than scientific inference. What these parallel headlines accomplish is context. They remind us that astronomy in 2025 is extraordinarily active, with multiple frontiers advancing simultaneously. JWST is revolutionizing exoplanet characterization and early universe studies. Solar observatories are revealing complex magnetohydrodynamics of stellar activity. Cosmological surveys are mapping the universe's large-scale structure with unprecedented precision. Gravitational wave detectors are catching colliding black holes weekly. Neutrino telescopes are probing stellar cores and supernovae. And amidst all this, interstellar object studies are emerging as a new subfield, connecting dynamical astronomy with planetary science, galactic archaeology, and astrobiology. The richness of this landscape argues for patience and perspective. 3i Atlas is one puzzle piece in a vast jigsaw where most pieces haven't been found yet, let alone placed. Demanding immediate answers or definitive conclusions is unrealistic. Science advances incrementally, each observation adding constraints, each measurement narrowing possibilities, each debate refining hypotheses. The process frustrates those who want quick resolutions, but it's robust and self-correcting in ways that hasty consensus would not be. And perhaps most importantly, the parallel discoveries demonstrate that the universe is endlessly fascinating, regardless of whether specific anomalies prove mundane or revolutionary. Whether 3i Atlas is a natural comet or an artificial probe, whether K218b hosts life or just complex chemistry, whether Euclid's structures require new physics or just better simulations, the universe remains a source of wonder, mystery and intellectual challenge that justifies our attention and effort regardless of how individual questions resolve. We study not because we expect every observation to overturn physics, but because we're curious, because understanding brings satisfaction, and because occasionally, very occasionally, we do stumble across something genuinely new that reshapes how we think about reality. Until then, the work continues, data accumulates, and mysteries like 3i Atlas keep us engaged, frustrated, and endlessly curious about what lies beyond our current knowledge. Part 14. Synthesis. What 3i Atlas seems to tell us. We've journeyed through observations, anomalies, hypotheses, and context. Now comes the difficult work of synthesis, assembling disparate pieces into coherent picture, acknowledging what we know, admitting what we don't, and identifying what matters most as 3i Atlas's story continues to unfold. This is where science reveals its true character, not through definitive answers, but through honest assessment of evidence, uncertainty, and next steps. The ExoMars image, where we began, remains emblematic. It showed an object that doesn't look like textbook predictions suggested it should. No visible tail despite active coma, no elongation despite expected dust production, just a compact fuzzball that could almost pass for a distant galaxy, except for its motion against background stars. This visual discordance sets the tone for everything that followed. 3i Atlas systematically defies expectations while remaining within bounds of natural possibility. The spectroscopic data revealed carbon dioxide dominance 8 times greater than water vapour, inverting the typical cometary ratio and suggesting either unusual formation environment, perhaps the thick disk origin, perhaps metal-poor protoplanetary chemistry, or preferential volatile loss during millions of years wandering interstellar space. Either explanation is natural and plausible, yet both push 3i Atlas toward the statistical edges of cometary populations, marking it as unusual, even among already rare interstellar visitors. The polarimetry showed extreme negative branch reaching -2.7%, significantly deeper than typical comets, and implying either highly porous dust aggregates, exotic grain compositions, or surface coatings that alter scattering properties. Combined with red-sloped reflectance spectra suggesting carbonaceous or organic-rich dust, these optical properties paint a picture of material that doesn't quite match solar system analogues. Again, not impossible, but unusual. The rotational light curve revealed 16-hour period with modest amplitude, suggesting elongated but not extreme nucleus shape, consistent with natural tumbling under angular momentum conservation. The rotation itself is reassuring. It behaves like natural objects do, spinning under physics' inexorable laws without hints of active stabilization or controlled attitude, changes that might suggest artificial systems. The dynamical measurements remain contested, with some analyses showing forward-directed non-gravitational acceleration, consistent with Loeb's claims, others finding perpendicular forces consistent with standard cometary jets, and still others arguing that measurement uncertainties are too large for confident detection. This ambiguity reflects the difficulty of precise astrometry on faint, fast-moving targets, and will resolve only with extended observations providing longer-time baselines. The origin modelling pointing toward thick disk ancestry adds profound context. If 3i Atlas truly formed 8 to 12 billion years ago around metal-poor stars in the galactic thick disk, it carries chemical signatures from epochs when the universe was younger, stars were different, and planetary systems formed under conditions alien to our solar system's relatively metal-rich environment. This makes every anomaly more understandable, not as violations of natural law, but as expressions of natural diversity arising from formation environments we've never sampled before. The unusual chemistry isn't a puzzle requiring exotic solutions. It's a window into ancient galactic conditions that we're privileged to study through this wandering ambassador from the deep past. Synthesizing these elements into coherent narrative requires acknowledging multiple viable interpretations. The conservative synthesis goes like this. 3I Atlas is a natural comet from the thick disk, ejected from its parent system millions to billions of years ago, carrying compositional signatures reflecting low metallicity formation chemistry, with dust properties altered by prolonged cosmic ray and ultraviolet exposure during interstellar transit, exhibiting weak tail formation due to large grain sizes or cohesive aggregates, observed under unfortunate viewing geometry that foreshortens or hides the tail that physically exists, with modest activity levels consistent with aged, processed surface ices that sublimate weakly compared to fresh solar system comets. This explanation requires no new physics, invokes only processes we've observed or theorized elsewhere, and treats 3I Atlas as unusual but natural, a statistical outlier within permitted parameter space rather than a fundamental challenge to our understanding. Most astronomers favour this synthesis, seeing it as parsimonious and scientifically responsible. The anomalies don't vanish in this telling, but they're contextualized as expected variations in a diverse population we're only beginning to sample adequately. The provocative synthesis acknowledges the same observations but weighs them differently. It notes that multiple independent anomalies, composition, polarization, missing tail, possible forward acceleration, all appear in the same object, creating a pattern that strains coincidence even while each individual feature admits natural explanation. It emphasizes that ESA's urgent response, including JUICE retasking, suggests institutional recognition that something about 3I Atlas warrants exceptional attention beyond routine interstellar object characterization. It leaves space for possibilities we haven't fully considered, perhaps new dust physics, perhaps exotic chemical pathways, perhaps even, though this remains deeply speculative, technological origins. This synthesis doesn't claim proof of anything exotic, but maintains that premature closure, declaring the mystery solved before key observations are complete, risks missing genuine discovery if 3I Atlas truly represents something beyond current frameworks. It advocates for continued scrutiny, additional observations and intellectual openness to interpretations that might initially seem improbable, but become more credible as evidence accumulates. Between these poles lies the pragmatic synthesis. We don't know yet, the data are ambiguous, the observations incomplete, and patience is warranted until upcoming milestones provide additional constraints. JUICE. Imaging might reveal tail formation as viewing geometry changes. Perihelion observations might show activity surge that clarifies dust production mechanisms. Long-term astrometry might definitively characterize non-gravitational forces. Continued spectroscopy might find additional molecular species diagnostic of formation environment or processing history. Each of these observations could shift interpretation significantly. A visible tail appearing in JUICE data would resolve the central visual anomaly, suggesting the ExoMars observations simply caught 3I Atlas at an unfortunate angle or activity minimum. Perihelion spectra showing isotopic ratios consistent with ancient low metallicity stellar environments would confirm thick disk origin and naturalize the compositional oddities. Conversely, persistent tail absence despite maximum solar heating would deepen the mystery, forcing more creative explanations about why an actively outgassing object produces no visible tail. The prediction for upcoming months is straightforward. More data will clarify some questions while raising new ones. This is astronomy's typical trajectory. Observations answer specific queries, but reveal unexpected complexities requiring additional study. 3I Atlas won't suddenly become simple and fully understood. More likely, our picture will become simultaneously more detailed and more nuanced, with some anomalies resolving naturally while others persist or transform into different puzzles. Ground observatories will continue photometry and spectroscopy as 3I Atlas moves through its orbit. The object will brighten as it approaches perihelion, improving signal-to-noise and enabling measurements currently impossible at its faint magnitudes. Spectroscopists will hunt for isotopic signatures, carbon-13 to carbon-12 ratios, oxygen-18 abundances, deuterium to hydrogen fractions, that reveal nucleosynthetic histories and formation temperatures. These ratios are extraordinarily diagnostic, encoding information about parent star metallicity, disk temperature gradients, and chemical processing that unambiguously identifies formation environments. The public key to understanding 3I Atlas is recognizing that we're witnessing science in real time, with all its uncertainty, debate, and gradual refinement. There's no conspiracy of silence, no hidden data proving aliens, no secret knowledge withheld from public consumption. What you see, contested measurements, competing interpretations, honest acknowledgement of ambiguity, is authentic scientific process. It's messy because reality is complex, uncertain because measurements are difficult, and debated because reasonable people interpret ambiguous data differently based on their priors and expertise. This transparency is valuable even when frustrating. It teaches that science isn't a collection of facts, but a method for approaching truth through systematic observation, careful reasoning, and communal debate. 3I Atlas becomes a case study in how this method operates when confronting genuine mystery, not the manufactured mystery of conspiracy theories or pseudoscience, but the real uncertainty arising when nature presents configurations we haven't encountered before and must puzzle out through patient observation and careful thought. The suspense question persists. What if the anomalies don't resolve naturally? What if JUICE confirms tail absence? Spectroscopy reveals impossible isotopes, dynamics show acceleration unexplainable by outgassing, and the accumulation of evidence forces consideration of hypotheses currently dismissed as too exotic. At what point does unusual but natural become, we need radically different explanations? Science doesn't have a predetermined threshold, only collective judgment that emerges through publication, peer review, conference debates, and gradual consensus building. That collective judgment is currently weighted toward natural explanations, but it remains responsive to evidence. If future observations definitively rule out conventional cometary behaviour, tail formation impossible under any geometry, acceleration incompatible with sublimation physics, materials requiring technologies we don't possess, then the judgment will shift. Not easily, not quickly, but eventually and inevitably, because science's strength lies in its self-correcting nature, its willingness to revise when data demands revision. For now, 3I Atlas occupies liminal space between mundane and extraordinary, between explainable and mysterious, between patience and impatience. It invites us to sit with uncertainty, to resist premature conclusions, to maintain intellectual humility before complexity. These are difficult disciplines in a culture that craves quick answers and definitive statements, but they're essential disciplines for anyone who wants to understand how we actually learn about the universe rather than how we imagine we do. The synthesis, then, is fundamentally one of openness to evidence, to revision, to surprise. 3I Atlas appears to be a natural comet from exotic origins exhibiting unusual but perhaps explicable properties. Or it's something stranger that we'll understand only after accumulating more data and expanding our theoretical frameworks. The honest answer is, we don't fully know yet. We're working on it, and that uncertainty is exactly where science lives most vibrantly. Part 15. Big Picture Implications, Risks and What to Watch. Every scientific observation carries implications beyond its immediate scope, radiating outward through connected domains of knowledge, and occasionally touching questions we didn't expect to confront. 3I Atlas, regardless of how its anomalies ultimately resolve, has already generated implications worth considering for cometary science, interstellar object populations, planetary system diversity, and even the long-shot possibility of detecting technological artifacts through astronomical surveys. If 3I Atlas proves entirely natural, the implications remain significant. It would demonstrate that interstellar comets exhibit compositional and behavioural diversity exceeding what solar system comets show, reflecting the full range of formation environments across the galaxy's history. This diversity would validate the hypothesis that each planetary system is somewhat unique, shaped by its star's metallicity, the disk's chemical inventory, the giant planet's migration history, and countless other variables that differ system to system. Astronomy would gain a richer taxonomy of cometary objects, expanding from solar system-centric categories to galactic-scale classification schemes that accommodate metal-poor objects, carbon-rich objects, ancient processed objects, and other categories we haven't yet imagined. This expansion would benefit comet physics by providing natural experiments, objects formed under different conditions testing our models' predictions about how composition affects activity, how dust properties depend on formation chemistry, how sublimation dynamics vary with volatile ratios. Each well-characterized interstellar visitor becomes a data point refining theories, gradually transforming comet science from descriptive to predictive, from case-by-case interpretation to robust statistical framework. If anomalies persist and resist natural explanation, the implications escalate dramatically. Persistent tail absence despite vigorous outgassing would force reconsideration of dust production mechanisms, perhaps revealing new physics of grain aggregation or electrostatic effects that current models don't capture. Forward acceleration incompatible with sublimation would suggest forces we haven't identified, perhaps solar wind coupling more efficient than thought, perhaps magnetic fields interacting with ionized coma in unexpected ways, perhaps radiative forces on asymmetric bodies producing non-intuitive accelerations. These would still be natural phenomena, but they'd expand our understanding of what natural encompasses, adding complexity and nuance to frameworks we thought were mature. Science progresses through such expansions, each anomaly ultimately resolved through deeper understanding rather than abandonment of natural laws. The history of astronomy is filled with examples. Neptune's existence inferred from Uranus's anomalous orbit, dark matter postulated to explain galactic rotation curves, dark energy invoked to account for cosmic acceleration. Anomalies drive discovery when approached with rigor and creativity. The most transformative implications arise if 3I Atlas proves artificial, though this remains highly improbable given current evidence. Detection of technological artifacts would constitute the most significant discovery in human history, instantly answering whether we're alone in the universe, while raising countless new questions about the prevalence, nature and fate of technological civilizations. The implications would cascade through every domain: science, philosophy, theology, politics, culture, as humanity grapples with confirmed existence of other intelligences. But this outcome requires extraordinary evidence that doesn't yet exist. Geometric structures in high-resolution images, coherent electromagnetic emissions detected by radio telescopes, materials impossible to form naturally, dynamics that violate conservation laws or show controlled propulsion. None of these have been observed. Until they are, artificial origin remains speculative entertainment, rather than scientific hypothesis. The risks of this investigation are primarily reputational and resource allocation. Overhyping 3I Atlas as potentially artificial when evidence doesn't support that conclusion risks public disillusionment when mundane explanations emerge. Crying wolf too often trains people to ignore legitimate future discoveries, creating boy who cried wolf scenarios where genuine breakthroughs are dismissed as more hype. Scientists must balance openness to unexpected possibilities with responsibility to communicate honestly about probabilities and evidence quality. Resource allocation poses another risk. If 3I Atlas commands disproportionate attention and telescope time relative to its actual scientific value, other worthy projects suffer. Astronomy operates under constrained resources, limited observing time, limited funding, limited personnel. Every hour spent observing 3I Atlas is an hour not spent on exoplanet characterization, galaxy evolution studies, supernova follow-up, or countless other investigations. The decision to prioritize 3I Atlas must be justified by scientific merit, not public fascination or speculative possibilities. Conversely, underinvesting carries risks too. If 3I Atlas represents genuine anomaly requiring intensive study to understand, insufficient observations might allow it to depart before key measurements are completed, leaving permanent gaps in our knowledge. The object won't return. Interstellar visitors pass through once, never to be seen again. Missing the opportunity to characterize it thoroughly would be a failure of scientific priorities, a surrender to resource constraints when the stakes justify exceptional effort. The upcoming checkpoints are clear. Perihelion passage offers maximum activity and best observation conditions. JUICE imaging provides different viewing geometry and instrument capabilities. Long-term astrometry constrains dynamics definitively. Spectroscopic. Campaigns hunt for isotopic signatures and molecular species. Polarimetry refines dust properties. Each checkpoint will either resolve anomalies, confirm them, or transform them into different questions requiring new observations. What should the public watch for? Clear tail formation would signal conventional behaviour, demystifying 3i Atlas into interesting but natural category. Persistent tail absence despite maximum heating would deepen the mystery, forcing creative explanations. Isotopic ratios confirming ancient metal-poor origins would validate thick disk hypothesis and explain compositional oddities. Anomalous isotopes, perhaps deuterium ratios incompatible with any known stellar environment, would raise profound questions about origin and nature. Spectroscopic detection of complex organics might hint at prebiotic chemistry, tantalizing astrobiology even without proving biology. Detection of simple geometric structures in improved imaging would trigger intense scrutiny, though natural processes can produce surprisingly geometric features, hexagonal crater patterns, linear fractures, regularly spaced jets, so geometry alone wouldn't prove artificiality. Radio emissions at unnatural frequencies or showing modulation patterns inconsistent with plasma physics would be genuinely extraordinary, demanding immediate follow-up and independent confirmation. Most likely the resolution will be gradual and unsatisfying, no single observation definitively settling all questions, but accumulated evidence slowly shifting consensus toward natural explanations that accommodate 3i Atlas's peculiarities without requiring exotic hypotheses. The tail might appear faintly in later observations, explained as delayed onset due to surface crusts. The composition might be contextualized as typical for thick disk objects once we study more of them. The polarization might fit updated models incorporating ancient radiation processing. The story would end not with bang but with whimper, interesting footnote in cometary catalogues rather than paradigm-shifting revelation. But there's always the possibility, remote, improbable, yet non-zero, that 3i Atlas genuinely is something beyond our current frameworks. That possibility, however slight, justifies the attention, the scrutiny, the resources devoted to understanding it. Because if we're wrong about it being natural, if the anomalies prove intractable, if evidence accumulates forcing consideration of exotic alternatives, then the implications transcend astronomy entirely. We'd be confronting evidence that intelligence exists beyond Earth, that technology propagates between stars, that we're part of a broader cosmic community we've only glimpsed through this singular strange visitor. The final monologue brings us full circle. ESA's first image wasn't supposed to look like this. Tailless, compact, enigmatic. Yet there it was, pixels arranged in patterns that defied expectations while remaining within possibility's broad boundaries. And maybe that's the point. Maybe the universe is telling us through 3i Atlas and countless other anomalies that our models are provisional, our understanding incomplete, our categories too rigid to encompass reality's full diversity. Maybe the appropriate response isn't to force observations into existing boxes or immediately leap to exotic explanations, but to sit with mystery, investigate patiently, and remain open to whatever truth emerges from careful study. 3i Atlas continues its journey, racing through the inner solar system at 86 kilometers per second, oblivious to our scrutiny, our debates, our hopes and speculations. It will pass perihelion, perhaps flaring into activity or remaining stubbornly tailless, then recede toward the outer solar system and eventually back into interstellar space, rejoining the great slow circulation of matter between stars. We'll watch until it fades below detection, extracting every photon of information, every spectral line, every dynamical constraint. And then we'll wait for the next visitor, the fourth confirmed interstellar object, wondering whether it will behave conventionally or add new mysteries to the growing collection. That waiting is where we live now, between visitors, between observations, between hypothesis and confirmation. It's uncomfortable but honest, uncertain but exciting, frustrating but intellectually alive. This is how science actually works, how knowledge actually grows, how humanity actually learns about a universe that refuses to simplify itself for our convenience. 3i Atlas teaches patience, humility and wonder, not through definitive answers, but through questions that linger, observations that surprise, and the persistent possibility that sometimes, just sometimes, reality is stranger and more marvellous than we dared imagine.